Tonight, we journey through the complete story of planetary systems, from the swirling clouds of gas and dust where stars are born, to the remarkable diversity of worlds we have discovered orbiting other stars. Let yourself drift as we explore cosmic nurseries, rocky worlds, giant planets, and the eternal search for places like home among the stars. Far away from the familiar glow of city lights, beyond the gentle curve of our planet's atmosphere, and stretching across distances so vast that light itself requires years to traverse them, there exist enormous clouds of gas and dust that serve as the birthplaces of stars and their accompanying planetary systems. These cosmic nurseries, known as molecular clouds, are among the most beautiful and significant structures in our galaxy. They are the cradles from which all planetary systems, including our own, have emerged. As you settle into a comfortable position and allow your breathing to slow, let us journey together into these remarkable regions of space, where the story of every planet begins. Molecular clouds are truly enormous structures, spanning anywhere from a few light years to hundreds of light years across. To put this into perspective, a single light year represents the distance that light travels in 1 year, which amounts to approximately 5.88 trillion miles or 9.46 trillion kilometers. When we speak of clouds that stretch across dozens or even hundreds of these units, we are describing objects of almost incomprehensible scale. Within our own Milky Way galaxy, thousands of these clouds drift through the spiral arms, each one containing enough raw material to form thousands upon thousands of stars, along with their planetary companions. The composition of these molecular clouds is predominantly hydrogen, the simplest and most abundant element in the universe. Roughly 73% of the visible matter in the cosmos consists of hydrogen, and molecular clouds reflect this cosmic abundance. Within these clouds, hydrogen exists primarily in its molecular form, meaning two hydrogen atoms bonded together to create H2 molecules. This molecular hydrogen is accompanied by helium, which makes up most of the remaining mass, along with trace amounts of heavier elements and various molecular compounds. Carbon monoxide, water vapor, ammonia, and countless other molecules drift through these clouds, each one destined to play a role in the formation of future planetary systems. The temperatures within molecular clouds are extraordinarily cold by any earthly standard. Deep within the densest regions of these clouds, temperatures can drop to merely 10 to 20 Kelvin, which translates to approximately negative 440 to negative 420 degrees Fahrenheit. At such extreme cold, molecular motion slows dramatically, and the cloud material becomes remarkably still and quiet. This frigid environment is essential for the process of star and planet formation, as warmer temperatures would cause the gas to expand and resist the gravitational collapse necessary to form new stellar systems. Despite their enormous size and mass, molecular clouds are incredibly diffuse by terrestrial standards. The density within a typical molecular cloud might be only a few hundred to a few thousand molecules per cubic centimetre. Compare this to the air you're breathing right now, which contains approximately 25 quintillion molecules in every cubic centimetre, and you begin to appreciate just how tenuous these cosmic clouds truly are. If you could somehow transport yourself into the heart of a molecular cloud, you would find it to be a better vacuum than anything we can create in laboratories here on Earth. Yet across the vast volumes of these clouds, even such sparse material accumulates into masses that dwarf our entire solar system. The process by which a portion of a molecular cloud begins to collapse and eventually form a star with its planetary system is both elegant and complex. It often begins with some external trigger that disturbs the delicate equilibrium within the cloud. This trigger might be the shockwave from a nearby supernova explosion. the passage of the cloud through one of the galaxy's spiral arms, or the gravitational influence of a neighbouring cloud or star. Whatever the cause, the disturbance creates regions of slightly higher density within the cloud, and these denser regions possess slightly stronger gravitational pull than their surroundings. Once a region of enhanced density forms within a molecular cloud, gravity begins its patient work of gathering more and more material. The denser region attracts nearby gas and dust, growing gradually more massive and more gravitationally influential. As more material falls inward, the region becomes denser still, and its gravitational reach extends further into the surrounding cloud. This process feeds upon itself in a beautiful example of positive feedback, with each increment of added mass making it easier to attract yet more material from the cloud. As the collapsing region gathers mass and shrinks in size, something remarkable begins to happen. The cloud of gas and dust does not simply fall straight inward toward the center of the collapse. Instead, any slight initial rotation in the original cloud material becomes amplified as the collapse proceeds. This phenomenon follows the same principle that causes a spinning ice skater to rotate faster when they pull their arms close to their body. Physicists call this the conservation of angular momentum, and it ensures that virtually every collapsing cloud region will spin faster and faster as it contracts. The increasing rotation of the collapsing material has a profound effect on the geometry of the collapse. Material falling inward along the rotation axis can proceed relatively unimpeded toward the center. However, material approaching from directions perpendicular to the rotation axis experiences an outward centrifugal effect that resists the inward pull of gravity. The result is that the collapsing cloud gradually flattens into a disc shape, with the material concentrated in a plane perpendicular to the rotation axis. This flattened structure is called a protoplanetary disk, and it represents the direct precursor to a planetary system. The formation of a protoplanetary disk is one of the most important steps in the creation of planets. Within this rotating disk of gas and dust, all of the raw materials needed to build planets are present and organized in a way that makes planet formation possible. The disk typically extends outward from the central protostar for hundreds of astronomical units, where one astronomical unit represents the average distance between Earth and the Sun, approximately 93 million miles, or 150 million kilometers. Across this vast expanse, conditions vary dramatically, from the hot inner regions close to the forming star to the frigid outer reaches where ices can survive. At the center of the protoplanetary disk, the protostar continues to grow as material from the disk spirals inward and falls onto its surface. The protostar is not yet a true star in the sense of sustaining nuclear fusion in its core, but it is well on its way to achieving that milestone. The gravitational energy released as material falls onto the protostar heats it to impressive temperatures, causing it to glow brightly in infrared light. This warmth from the central protostar establishes a temperature gradient across the disk, with regions closer to the star being considerably warmer than those farther away. The temperature structure of the protoplanetary disk has profound implications for the types of planets that can form at different distances from the central star. In the inner regions of the disk, where temperatures may exceed several hundred degrees, only materials with high melting points can exist in solid form. Rocky minerals, metal-like compounds, and certain oxides can survive as solid particles in these hot inner zones, but more volatile substances like water, ammonia, and methane exist only as gases. This means that planets forming in the inner disk have access primarily to rocky and metallic building materials. Farther from the central protostar, temperatures drop steadily with increasing distance. At a certain distance from the star, temperatures become cold enough for water ice to exist in solid form. This boundary is called the snow line or ice line, and it represents one of the most important divisions within a protoplanetary disk. Beyond the snow line, solid particles can incorporate not only rocky materials but also abundant water ice, dramatically increasing the total amount of solid material available for planet building. This enhanced supply of solids in the outer disk helps explain why the giant planets in our solar system formed in the cold outer regions rather than the warm inner zones. The dust particles within a protoplanetary disk are remarkably small, typically measuring only a micrometer or so in diameter, similar to the particles in cigarette smoke or fine talcum powder. These tiny grains are the fundamental building blocks from which all planets ultimately form. But the journey from micrometer-sized dust to 1,000-kilometer planets is extraordinarily long and complex. Understanding how this growth occurs has been one of the central challenges in the study of planetary formation, and researchers continue to refine their models as new observations provide additional constraints. The first step in the growth of solid bodies within a protoplanetary disk involves the gentle collision and sticking of dust particles. When two tiny dust grains collide at low velocities within the disk, they can adhere to one another through van der Waals forces, the same weak electromagnetic attraction that allows geckos to climb smooth walls. Through countless such collisions over thousands of years, dust particles gradually aggregate into larger and larger structures, progressing from individual grains to fluffy aggregates to more compact pebbles measuring centimeters to meters in size. This early phase of growth proceeds relatively smoothly, but significant challenges arise as particles grow to intermediate sizes. Pebbles and boulders measuring meters to tens of meters across face a serious problem known as the meter-size barrier. At these sizes, particles are large enough to experience significant aerodynamic drag from the gas in the disk, but not massive enough for their own gravity to play a significant role. The drag causes these intermediate-sized bodies to spiral inward toward a star on timescales of only a few hundred years, potentially removing them from the disk before they can grow larger. Additionally, collisions between meter-sized bodies tend to result in fragmentation rather than growth. When two boulders collide at the velocities typical of protoplanetary disks, they are more likely to shatter into smaller pieces than to stick together and form a larger body. This combination of rapid inward drift and destructive collisions presents a significant obstacle to planet formation, and explaining how this barrier is overcome has required considerable theoretical ingenuity. One promising mechanism for bypassing the meter-size barrier involves a process called streaming instability. Within a protoplanetary disk, solid particles tend to concentrate in certain regions due to their interaction with the gas. When the local concentration of particles becomes high enough, their collective gravity can trigger a rapid collapse, bringing together enough material to form bodies tens to hundreds of kilometers across in a single dramatic event. These bodies, called planetesimals, are large enough that their own gravity becomes the dominant factor in their subsequent evolution, allowing them to continue growing through gravitational attraction rather than simple sticking. The formation of planetesimals marks a crucial transition in the planet-building process. Once bodies reach sizes of tens of kilometers or more, they can begin sweeping up smaller debris in their vicinity through gravitational focusing. A planetesimal's gravity bends the trajectories of nearby particles, effectively increasing the cross-sectional area over which it can collect material. Larger planetesimals have stronger gravity and therefore larger effective collection areas, allowing them to grow faster than their smaller neighbours. This preferential growth of the largest bodies is called runaway accretion, and it leads to the rapid emergence of a small number of dominant bodies in each region of the disk. As the largest planetesimals continue to grow, they eventually reach sizes where they begin to gravitationally perturb the orbits of their neighbours. At this stage, the growth process transitions from runaway accretion to a phase called oligarchic growth. During oligarchic growth, a small number of large bodies called planetary embryos or protoplanets dominate each region of the disk. These embryos continue to grow by accreting planetesimals and smaller debris, but their mutual gravitational interactions stir up the velocities of nearby objects, making further growth more difficult. The result is a more orderly growth phase in which the largest bodies grow at similar rates, maintaining their relative sizes as they all increase in mass. Throughout this entire process of growth and accumulation, the protoplanetary disk is slowly being depleted. Material is consumed by the growing planets, accreted onto the central star, or expelled from the system by stellar winds and radiation pressure. Observations of young stellar systems suggest that protoplanetary disks typically survive for only a few million years before being largely dispersed. This relatively brief window of time places important constraints on planet formation, requiring that the basic architecture of a planetary system be established within this limited period. The dispersal of the protoplanetary disk marks the end of the main planet-building phase, but it does not mean that planetary systems stop evolving. The young planets that emerge from the disk continue to interact gravitationally with one another, and these interactions can lead to significant changes in their orbits over time. Collisions between planetary embryos may still occur, potentially building larger planets or tilting planetary rotation axes. The late stages of planet formation can be violent and chaotic, with the final configuration of a planetary system depending sensitively on the details of these complex gravitational interactions. As you rest quietly and let these images of cosmic creation drift through your mind, consider that every planet in the universe, including our own Earth, began its existence in a setting much like the one we have described. Swirling disks of gas and dust, illuminated by the warm glow of young stars, served as the nurseries in which worlds were born. The atoms that make up your body, the oxygen you breathe, the iron in your blood, all of these were once part of a protoplanetary disk orbiting a young star. We are, in a very real sense, children of the cosmic nurseries, our existence made possible by the patient processes of stellar and planetary formation that have operated throughout the universe for billions of years. Let this thought bring you a sense of connection to the cosmos as you continue to relax and drift. The story of planetary systems is ultimately our own story, written in the language of gravity, chemistry, and time across the vast canvas of space. And as we continue our journey through this narrative, we will see how these fundamental processes have given rise to an astonishing diversity of worlds, from the familiar planets of our own solar system to the exotic exoplanets that orbit distant stars. Our solar system, the planetary family to which Earth belongs, represents the most thoroughly studied example of a planetary system in the universe. For centuries, astronomers have observed, measured, and catalogued the objects that share our cosmic neighbourhood, building up a detailed picture of the Sun's extended family. As we explore the architecture of our solar system, we encounter a remarkable variety of worlds, each with its own unique character and history. Allow yourself to drift along as we take a leisurely tour through this familiar yet endlessly fascinating collection of planets, moons, and smaller bodies. At the centre of our solar system sits the Sun, a middle-aged yellow dwarf star that has been shining steadily for approximately 4.6 billion years. The Sun contains more than 99.8% of all the mass in the solar system, making it the gravitational anchor around which everything else revolves. Its diameter of approximately 864,000 miles makes it large enough to contain more than 1 million Earths, and its surface temperature of about 10,000 degrees Fahrenheit gives it the brilliant yellow-white glow that illuminates our days. Deep within the Sun's core, nuclear fusion reactions convert hydrogen into helium, releasing the energy that has sustained life on Earth for billions of years. Moving outward from the Sun, we first encounter the 4 inner planets, often called the terrestrial or rocky planets. These worlds share certain fundamental characteristics that distinguish them from their larger cousins in the outer solar system. They are composed primarily of rock and metal, they have solid surfaces that spacecraft can land upon, and they are relatively small compared to the giant planets. The terrestrial planets formed in the warm inner regions of the protoplanetary disk, where only materials with high melting points could exist as solids. Mercury, the innermost planet, orbits the Sun at an average distance of only 36 million miles, completing one circuit in just 88 Earth days. This small, dense world measures only 3.32 miles in diameter, making it barely larger than Earth's moon. Mercury's surface is heavily cratered, bearing the scars of billions of years of impacts from asteroids and comets. Without a substantial atmosphere to retain heat, Mercury experiences extreme temperature variations, with daytime temperatures soaring above 800 degrees Fahrenheit, while nighttime temperatures plunge to nearly negative 290 degrees Fahrenheit. Despite its harsh conditions, Mercury possesses a surprisingly large iron core that generates a weak but measurable magnetic field. Venus, the second planet from the Sun, orbits at a distance of approximately 67 million miles and is often called Earth's twin due to its similar size and mass. However, this comparison becomes deeply ironic upon closer examination, for Venus is one of the most hostile environments in the solar system. A dense atmosphere composed almost entirely of carbon dioxide creates a runaway greenhouse effect that raises surface temperatures to approximately 900 degrees Fahrenheit, hot enough to melt lead. Atmospheric pressure at the surface is roughly 90 times that of Earth, equivalent to the pressure found half a mile beneath Earth's oceans. Thick clouds of sulfuric acid shroud the planet in perpetual overcast, hiding the volcanic landscape below from direct observation. Earth, our home world, occupies the third orbital position at an average distance of 93 million miles from the Sun. This distance, combined with Earth's moderate size and the presence of a substantial atmosphere, creates conditions that have allowed liquid water to exist on the surface for billions of years. Earth is unique among the planets of our solar system in possessing large oceans of liquid water, a characteristic that has proven essential for the development and sustenance of life. Our planet's diameter of approximately 7,918 miles and its iron-nickel core generate a strong magnetic field that shields the surface from harmful solar radiation and cosmic rays. Earth is accompanied by a single large moon, simply called the Moon or Luna, which orbits at an average distance of about 239,000 miles. The Moon is unusually large relative to its parent planet, with a diameter of 2,159 miles, making the Earth-Moon system almost a double planet. The Moon's gravitational influence stabilizes Earth's axial tilt, moderating seasonal variations and contributing to the long-term climate stability that has benefited life on our world. The Moon's origin is believed to involve a giant impact early in Earth's history, when a Mars-sized body collided with the young Earth and ejected debris that eventually coalesced into our lunar companion. Mars, the fourth and outermost of the terrestrial planets, orbits the Sun at an average distance of approximately 142 million miles. This rust-coloured world, named for the Roman god of war due to its blood-red appearance in the night sky, has long captured human imagination as a potential abode for life. Mars is considerably smaller than Earth, with a diameter of only 4,212 miles, and its thin atmosphere of carbon dioxide provides little protection from solar radiation or temperature extremes. Surface temperatures on Mars average around -80 degrees Fahrenheit, though they can vary considerably depending on location and season. Despite its current cold and dry conditions, Mars shows abundant evidence of a warmer, wetter past. Ancient river valleys, lake beds, and mineral deposits formed by water all testify to a time when liquid water flowed across the Martian surface. Understanding what happened to Mars, how it transformed from a potentially habitable world into the frozen desert we see today, remains one of the central questions in planetary science. Mars possesses two small moons, Phobos and Deimos, which are likely captured asteroids rather than bodies that formed alongside the planet. Between the orbits of Mars and Jupiter lies a region called the asteroid belt, home to millions of rocky bodies ranging in size from small boulders to the dwarf planet Ceres, which measures approximately 90 miles in diameter. The asteroid belt represents material that never successfully assembled into a planet, largely due to the gravitational influence of nearby Jupiter. The total mass of all objects in the asteroid belt is surprisingly small, amounting to only about 4% of the Moon's mass. Despite their relatively modest total mass, asteroids provide valuable information about the early solar system, as many of them have remained largely unchanged since the era of planet formation. Beyond the asteroid belt, we enter the realm of the giant planets, worlds so massive and so different from the terrestrial planets that they almost seem to belong to a different category of object entirely. The giant planets formed in the cold outer regions of the protoplanetary disk, where abundant water ice supplemented the rocky materials available for planet building. Their enormous masses allowed them to capture vast quantities of hydrogen and helium gas from the disk, giving them compositions that more closely resemble the Sun than the rocky inner planets. Jupiter, the fifth planet from the Sun and the largest planet in our solar system, orbits at an average distance of approximately 484 million miles. This colossal world has a diameter of about 86,881 miles, large enough to contain more than 1,300 Earths. Jupiter's mass exceeds that of all other planets in the solar system combined, making it the dominant gravitational influence after the Sun itself. The planet's rapid rotation, completing one turn in just under 10 hours despite its enormous size, creates pronounced equatorial bulging and drives powerful atmospheric circulation patterns. Jupiter's atmosphere displays a stunning array of colourful bands and swirling storms. The most famous of these storms is the Great Red Spot, an anticyclonic vortex that has been raging for at least 350 years and possibly much longer. This enormous storm is large enough to swallow Earth entirely, though recent observations suggest it has been gradually shrinking over the past century. The bands that stripe Jupiter's visible surface represent alternating zones of rising and sinking atmosphere, with lighter zones corresponding to higher, cooler clouds and darker belts to lower, warmer regions. Jupiter possesses an extensive system of moons, with 95 confirmed satellites as of recent counts. The four largest, discovered by Galileo Galilei in 1610, are called the Galilean moons, and are worlds of considerable interest in their own right. Io, the innermost Galilean moon, is the most volcanically active body in the solar system, its interior heated by tidal forces from Jupiter's immense gravity. Europa, the second Galilean moon, possesses a smooth icy surface beneath which lies a global ocean of liquid water, making it one of the most promising places to search for extraterrestrial life. Ganymede, the largest moon in the solar system, exceeds even Mercury in diameter and possesses its own magnetic field. Callisto, the outermost Galilean moon, displays an ancient, heavily cratered surface that has changed little over billions of years. Saturn, the sixth planet from the Sun, orbits at an average distance of approximately 886 million miles and is perhaps the most visually stunning object in the solar system. While Saturn itself is an impressive gas giant with a diameter of about 70,366 miles, it is the planet's magnificent ring system that captures the imagination. Saturn's rings extend outward for hundreds of thousands of miles, yet are remarkably thin, typically measuring only about 30 feet in thickness. The rings are composed primarily of water ice particles, ranging in size from tiny grains to house-sized chunks, all orbiting Saturn in a flattened disk. The origin of Saturn's rings remains a subject of active research. One possibility is that they formed from the debris of a moon or comet that ventured too close to Saturn and was torn apart by tidal forces. Another hypothesis suggests that the rings are primordial, dating back to the formation of the Saturn system itself. Recent data from the Cassini spacecraft, which orbited Saturn from 2004 to 2017, suggests that the rings may be relatively young in astronomical terms, perhaps only 100 million years old, though this conclusion remains somewhat controversial. Saturn's moon system rivals Jupiter's in complexity, with 146 confirmed satellites. The largest, Titan, is the second largest moon in the solar system, and the only moon known to possess a dense atmosphere. Titan's atmosphere is composed primarily of nitrogen, like Earth's, but surface temperatures of around negative 290 degrees Fahrenheit allow methane and ethane to exist as liquids. Titan possesses lakes and seas of liquid hydrocarbons, making it the only body in the solar system other than Earth known to have stable bodies of liquid on its surface. Another notable Saturnian moon is Enceladus, a small icy world that vents plumes of water vapour and ice particles from its south polar region, indicating the presence of a subsurface ocean. Uranus, the seventh planet from the Sun, orbits at an average distance of approximately 1.78 billion miles and represents a different class of giant planet than Jupiter and Saturn. While still much larger than Earth, with a diameter of about 31,518 miles, Uranus is considerably smaller than the gas giants and possesses a higher proportion of heavier elements. Astronomers often classify Uranus and Neptune as ice giants to distinguish them from the gas giants Jupiter and Saturn. The term ice refers not to frozen water on the surface, but to the abundance of water, ammonia, and methane in the planet's interior. Uranus possesses one of the most unusual characteristics of any planet in our solar system: its extreme axial tilt. While most planets rotate with their axes roughly perpendicular to their orbital planes, Uranus rotates on its side, with an axial tilt of approximately 98 degrees. This means that Uranus essentially rolls around the Sun rather than spinning like a top, causing extreme seasonal variations over its 84-year orbital period. The cause of this dramatic tilt is believed to be one or more giant impacts early in the planet's history that knocked it over onto its side. Neptune, the eighth and outermost planet in our solar system, orbits at an average distance of approximately 2.8 billion miles from the Sun. At this vast distance, sunlight takes over 4 hours to reach Neptune, and the planet receives only about 1,000th the solar energy that Earth does. Despite this limited energy input, Neptune's atmosphere displays surprisingly active weather patterns, including the fastest winds measured on any planet, reaching speeds of over 1,200 miles per hour. Neptune's blue colour results from methane in its atmosphere, which absorbs red light and reflects blue. Neptune possesses 16 known moons, the largest of which is Triton. This unusual moon orbits Neptune in a retrograde direction, meaning it moves opposite to the planet's rotation, strongly suggesting that Triton was captured from the Kuiper belt rather than forming alongside Neptune. Triton possesses a thin atmosphere and displays active geysers that erupt nitrogen gas and dark particles from beneath its frozen surface. The moon's retrograde orbit is gradually decaying, and in the distant future, Triton will spiral inward until tidal forces tear it apart, potentially creating a ring system around Neptune. Beyond Neptune lies the Kuiper belt, a vast region of icy bodies that extends from Neptune's orbit at about 30 astronomical units to approximately 50 astronomical units from the Sun. The Kuiper belt is home to thousands of known objects and potentially millions more awaiting discovery. These icy bodies are remnants from the formation of the solar system, preserved in the deep freeze of the outer solar system for billions of years. The most famous Kuiper belt object is Pluto, which was considered the ninth planet from its discovery in 1930 until its reclassification as a dwarf planet in 2006. Pluto, with a diameter of approximately 1,473 miles, is accompanied by 5 known moons, the largest of which is Charon. Charon is so large relative to Pluto that the two bodies actually orbit a common centre of mass located between them, making them sometimes referred to as a double dwarf planet system. The New Horizons spacecraft flew past Pluto in 2015, revealing a surprisingly complex and geologically active world with nitrogen ice glaciers, towering water ice mountains, and a thin atmosphere that freezes and falls as snow during the long Plutonian winter. Even farther from the Sun lies the scattered disk, a region of icy bodies on highly elliptical and inclined orbits that extend far beyond the main Kuiper belt. Objects in the scattered disk were likely placed on their current orbits by gravitational interactions with Neptune during the early history of the solar system. The most distant known object in our solar system, a dwarf planet candidate nicknamed Farfaroot, lies approximately 132 astronomical units from the Sun at its current position, though its highly elliptical orbit carries it much closer at perihelion. At the very edge of the Sun's gravitational influence lies the hypothetical Oort cloud, a vast spherical shell of icy bodies that may extend halfway to the nearest star. The Oort cloud is believed to be the source of long-period comets, icy visitors that occasionally fall inward toward the Sun on orbits that take thousands or even millions of years to complete. No objects in the Oort cloud have been directly observed due to their extreme distance and small size, but the orbits of long-period comets provide indirect evidence for its existence. As you let your thoughts drift through this grand tour of our solar system, consider the remarkable diversity of worlds that share our cosmic neighbourhood. From the scorched surface of Mercury to the frozen plains of Pluto, from the volcanic fury of Io to the methane seas of Titan, our solar system contains an astonishing variety of environments and conditions. Each of these worlds has its own story, its own history, and its own mysteries waiting to be unravelled. The birth of a planet is not a single event, but rather a long and intricate process that unfolds over millions of years. From the first tiny dust grains sticking together in a protoplanetary disk to the final assembly of a mature planetary system, the journey involves countless steps, each building upon those that came before. The story of planet formation begins with the tiniest of building blocks, microscopic dust grains measuring only a micrometer or so across. These grains are composed of various materials depending on their location within the protoplanetary disk. In the hot inner regions, close to the young star, dust grains consist primarily of silicate minerals and metallic compounds that can withstand high temperatures. Farther from the star, beyond the snow line, where temperatures drop below the freezing point of water, ice-coated grains become increasingly common. These icy particles will eventually contribute to the formation of the giant planets and their moons. The first step in the growth of solid bodies involves a gentle collision and adhesion of dust grains. Within the protoplanetary disk, dust particles are not stationary, but rather drift and tumble through the gas, occasionally encountering other particles. When two grains collide at sufficiently low velocities, they can stick together through surface forces, beginning the long process of growth. The exact mechanisms of adhesion vary depending on the composition and properties of the grains, but van der Waals forces, electrostatic attraction, and the stickiness of organic coatings all play roles in binding particles together. As dust grains stick together, they form larger and larger aggregates with increasingly complex structures. Initially, these aggregates are fluffy and porous, with large amounts of empty space between the constituent grains. A dust aggregate might contain only a few % solid material by volume, with the rest being vacuum. This fluffy structure actually aids continued growth, as the extended surface area provides more opportunities for capturing additional particles. Over time, collisions and compaction gradually reduce the porosity of these aggregates, producing more compact structures. The growth of dust aggregates proceeds through several distinct phases, each characterized by different physical processes and growth rates. In the earliest phase, growth is dominated by Brownian motion, the random jiggling of particles due to collisions with gas molecules. Brownian motion causes dust grains to wander through the disk, occasionally encountering and sticking to other grains. This process is relatively slow but effective for the smallest particles, gradually building up aggregates measuring tens to hundreds of micrometers across. As particles grow larger, other sources of relative motion become more important than Brownian motion. Turbulence within the protoplanetary disk creates eddies and currents that carry particles along, causing them to collide with other particles moving in different directions. Differential settling toward the disk midplane also creates relative velocities between particles of different sizes, as larger particles settle faster than smaller ones. These processes accelerate growth, allowing particles to reach millimeter and centimeter sizes within relatively short timescales. The growth of particles to centimeter sizes and beyond brings new challenges and opportunities. At these sizes, particles begin to experience significant aerodynamic drag from the gas in the disk. The gas orbits the central star at slightly less than the Keplerian velocity due to pressure support, while solid particles would naturally orbit at the full Keplerian velocity. This velocity difference creates a headwind that the particles experience as they orbit, causing them to lose angular momentum and spiral slowly inward toward the star. This inward drift poses a significant problem for planet formation, particularly for particles in the size range from centimeters to meters. Objects in this size range experience strong drag, but are not massive enough for their own gravity to play a significant role. The drift timescale for meter-sized boulders can be as short as a few hundred years, potentially removing them from the disk before they can grow into larger bodies. This challenge, known as the meter-sized barrier, has motivated extensive research into mechanisms that might allow particles to bypass this problematic size range. One important mechanism for overcoming the meter-sized barrier involves the concentration of particles in certain regions of the disk. Various processes can cause solid particles to accumulate in localized areas, increasing the local density of solids far above the average. Pressure bumps in the disk, created by variations in the gas distribution, can trap particles and prevent their inward drift. Vortices, rotating structures within the disk gas, can also concentrate particles in their centers. When the local density of particles becomes high enough, their collective gravity can trigger rapid gravitational collapse. The streaming instability represents one of the most promising mechanisms for concentrating particles and triggering gravitational collapse. This instability arises from the interaction between solid particles and the gas in the disk. When particles begin to concentrate in certain regions, they reduce the local gas velocity, which in turn reduces the headwind experienced by the particles. This allows the particles to concentrate further, creating a positive feedback loop that can rapidly amplify small initial density variations into dramatic concentrations of solid material. When a region of concentrated particles becomes dense enough, gravity takes over and triggers rapid collapse. Within a matter of years to decades, the concentrated particles fall together and merge into a single body measuring tens to hundreds of kilometers across. These bodies, called planetesimals, represent a crucial milestone in planet formation. Unlike the smaller particles that preceded them, planetesimals are massive enough that their own gravity dominates their subsequent evolution. They no longer experience significant aerodynamic drag and can persist in the disk indefinitely, growing through gravitational attraction rather than surface sticking. The formation of planetesimals marks the transition from a growth regime dominated by surface forces and aerodynamics to one governed primarily by gravity. Once planetesimals exist within a protoplanetary disk, they begin interacting with one another through their mutual gravitational attraction. These interactions determine how planetesimals collide, merge, and eventually assemble into full-sized planets. The gravitational dynamics of planetesimal populations are complex and fascinating, involving a delicate interplay between attraction, orbital mechanics, and random chance. Planetesimals do not simply drift through the disk, waiting to collide with one another. Instead, they follow elliptical orbits around the central star, with each planetesimal tracing its own unique path through space. The orbits of nearby planetesimals gradually become intertwined through gravitational perturbations, causing their paths to cross and creating opportunities for collisions. The rate at which collisions occur depends on the number of planetesimals present, their sizes, and the distribution of their orbital parameters. A crucial concept in understanding planetesimal collisions is gravitational focusing. When two planetesimals approach one another, their mutual gravitational attraction bends their trajectories, pulling them toward one another. This gravitational deflection effectively increases the cross-sectional area over which a collision can occur, making collisions more likely than they would be for non-gravitating bodies of the same size. The enhancement factor due to gravitational focusing can be substantial, particularly for large planetesimals with strong gravitational fields and for encounters occurring at relatively low velocities. The importance of gravitational focusing leads to a phenomenon called runaway growth. Consider a population of planetesimals with a range of sizes. The largest planetesimals have the strongest gravitational fields and therefore the largest gravitational focusing factors. This means they sweep up material from a larger effective area than smaller planetesimals, allowing them to grow faster. As they grow, their gravitational focusing factors increase further, accelerating their growth even more. The result is a positive feedback loop in which the largest bodies grow increasingly dominant, pulling away from the rest of the population in a runaway fashion. During the runaway growth phase, a small number of large bodies emerge from the initial planetesimal population and begin to dominate their local regions of the disk. These growing bodies, sometimes called planetary embryos or protoplanets, can reach sizes of hundreds to thousands of kilometers within a relatively short time. The runaway growth phase is characterized by rapid and dramatic increases in the sizes of the largest bodies, while smaller planetesimals grow much more slowly or not at all. As planetary embryos continue to grow, the dynamics of the system gradually change. The gravitational influence of the largest bodies begins to stir up the velocities of nearby planetesimals, increasing the average speed at which objects move relative to one another. Higher relative velocities reduce the effectiveness of gravitational focusing, because faster-moving objects are harder to deflect into collision courses. This velocity stirring eventually brings the runaway growth phase to an end, transitioning the system into a new regime called oligarchic growth. During oligarchic growth, a relatively small number of planetary embryos dominate the disk, each one controlling a feeding zone around its orbit. The embryos continue to grow by accreting planetesimals that wander into their feeding zones, but the growth rate is now regulated by the rate at which new planetesimals diffuse into these zones from elsewhere in the disk. The velocity stirring caused by the embryos keeps the planetesimal population dynamically hot, meaning that planetesimals have relatively high random velocities that reduce collision rates. An important characteristic of oligarchic growth is that it tends to produce roughly equal-sized embryos spaced at regular intervals throughout the disk. The spacing between embryos is determined by their gravitational reach, with each embryo dominating a region extending several Hill radii on either side of its orbit. The Hill radius is a measure of the distance over which a body's gravity dominates over the gravity of the central star, and it increases with the mass of the body. As embryos grow, their Hill radii expand, and the spacing between them adjusts accordingly. The oligarchic growth phase continues until the supply of planetesimals in the disk becomes depleted. As the embryos consume the available solid material, their growth rates slow and eventually cease. At this point, the disk contains a population of planetary embryos, each one containing a significant fraction of the solid material originally present in its feeding zone, along with a residual population of smaller planetesimals that have not yet been accreted. The total number of embryos depends on the properties of the original disk, but typical estimates suggest dozens to hundreds of embryos might form in a disk like the one that produced our solar system. The planetary embryos that emerge from oligarchic growth are not yet the final planets of the system. They are typically much smaller than the terrestrial planets we observe today, with masses perhaps 1/10 to 1/100th that of Earth. To build full-size terrestrial planets, these embryos must undergo a final phase of growth involving collisions and mergers among themselves. This final assembly phase is dramatically different from the earlier growth phases, involving giant impacts between roughly equal-sized bodies rather than the gradual accumulation of small particles. The transition from oligarchic growth to the giant impact phase is triggered by the dispersal of the gaseous component of the protoplanetary disk. While gas remains in the disk, it provides a damping effect that keeps the orbits of planetary embryos relatively circular and well separated. When the gas disperses, typically within a few million years of the star's formation, this damping effect disappears. Without gas damping, gravitational interactions among the embryos gradually excite their orbital eccentricities, causing their orbits to become more elongated and to cross one another. Once embryo orbits begin to cross, collisions become inevitable. The giant impact phase is characterized by a series of violent collisions between planetary embryos, each impact potentially doubling or tripling the mass of the surviving body. These collisions occur at velocities of several kilometers per second, releasing enormous amounts of energy and often completely melting both colliding bodies. The debris from these impacts can form disks around the surviving body, potentially giving rise to moons like Earth's moon. The giant impact phase is inherently chaotic and unpredictable. Small differences in the initial positions and velocities of embryos can lead to dramatically different outcomes, with some embryos surviving to become planets, while others are destroyed or ejected from the system. Computer simulations of this phase typically produce planetary systems with 3 to 5 terrestrial planets, broadly consistent with the 4 terrestrial planets in our own solar system. However, the specific properties of the resulting planets, including their masses, orbital parameters, and compositions, vary widely between different simulation runs. The formation of giant planets follows a somewhat different path than the formation of terrestrial planets. In the standard core accretion model, giant planet formation begins similarly to terrestrial planet formation, with the growth of a solid core through planetesimal accretion. However, giant planet cores form in the outer regions of the disk, beyond the snowline, where the abundance of solid material is enhanced by the presence of water ice. This enhanced solid abundance allows cores to grow larger than their counterparts in the inner disk. When a growing core reaches a critical mass, estimated at roughly 10 Earth masses, a dramatic transformation occurs. At this point, the core's gravity becomes strong enough to capture and retain large quantities of hydrogen and helium gas from the surrounding disk. Gas begins to flow onto the core, initially slowly, but with increasing rapidity as the growing planet's gravity strengthens. This runaway gas accretion can add hundreds of Earth masses of gas to the planet within a relatively short time, transforming a rocky core into a gas giant like Jupiter. The runaway gas accretion phase continues until one of two things happens. Either the planet opens a gap in the disk by gravitationally clearing material from its orbital vicinity, or the disk itself disperses before accretion is complete. Planets that complete their runaway accretion before the disk disperses become gas giants like Jupiter and Saturn, with masses dominated by hydrogen and helium. Planets that experience disk dispersal during their growth phase end up as ice giants, like Uranus and Neptune, with substantial gas envelopes, but composition still dominated by heavier elements. An alternative model for giant planet formation, called disk instability, proposes that giant planets can form directly from the gravitational collapse of dense regions in the protoplanetary disk. In this scenario, the disk develops spiral arms, or other density structures that become gravitationally unstable and collapse to form giant planets in a single dramatic event. Disk instability can potentially form giant planets very rapidly, within thousands of years rather than the millions of years required by core accretion. The disk instability model is particularly attractive for explaining giant planets that orbit very far from their stars, where the timescales for core accretion may be prohibitively long. However, disk instability requires specific conditions to operate, including relatively massive and cool disks that are prone to gravitational instability. The relative importance of core accretion and disk instability in forming the giant planet population remains an active area of research, with evidence suggesting that both mechanisms may operate in different circumstances. Throughout the planet formation process, the growing planets interact gravitationally with the disk of gas and dust from which they are forming. These interactions can cause planets to migrate, changing their orbital distances from the central star. Planetary migration has profound implications for the final architecture of planetary systems, potentially explaining why some giant planets are found very close to their stars despite having formed much farther out. Two main types of planetary migration have been identified. Type 1 migration affects smaller planets that are not massive enough to open gaps in the disk. These planets experience gravitational torques from the disk material, with spiral density waves generated by the planet carrying angular momentum away from or toward the planet. The net effect of these torques typically causes inward migration, though outward migration is possible under certain conditions. Type 1 migration can be quite rapid, with migration timescales shorter than the disk lifetime, raising questions about how planets avoid falling into their host stars. Type 2 migration affects larger planets that have opened gaps in the disk. Once a gap is opened, the planet becomes locked to the viscous evolution of the disk, migrating inward as the disk material slowly accretes onto the central star. Type 2 migration is typically slower than Type 1 migration, but it can still move planets significant distances over the lifetime of the disk. The combination of Type 1 and Type 2 migration can dramatically reshape planetary systems, moving planets far from their birthplaces. The complex interplay of accretion, migration, and gravitational interactions means that the final configuration of a planetary system may bear little resemblance to the initial distribution of solid material in the protoplanetary disk. Planets can end up much closer to or farther from their stars than where they formed. Multiple planets can become trapped in orbital resonances, with their orbital periods forming simple integer ratios. Some planets may be ejected from the system entirely, becoming free-floating rogue planets that wander through interstellar space. As the protoplanetary disk gradually disperses, the main phase of planet formation comes to an end. The young planetary system that emerges from this process may still undergo significant evolution, with gravitational interactions among planets potentially causing orbital instabilities and rearrangements. However, the basic architecture of the system, including the number of planets, their approximate masses, and their general orbital configuration, is largely established by the time the disk disappears. Let these images of cosmic construction drift through your mind as you continue to relax. The formation of planets is a story of patience and persistence, of tiny grains gradually assembling into worlds over millions of years. Every planet in the universe, from the smallest rocky world to the largest gas giant, has passed through these stages of growth and transformation. The processes we have described are operating right now, at this very moment, in protoplanetary disks throughout our galaxy, giving birth to new worlds that will one day shine in the skies of distant civilizations. Among the many types of worlds that populate planetary systems, rocky planets hold a special place in our imagination. These are the worlds with solid surfaces, the places where a spacecraft might land and a future explorer might someday walk. Rocky planets, also called terrestrial planets, after the Latin word for Earth, are built primarily from silicate rocks and metallic iron, the high-temperature materials that could survive in the warm inner regions of protoplanetary disks. As we explore the nature of rocky worlds, let yourself drift along and imagine standing on the surfaces of these distant and varied places. The fundamental characteristic that defines a rocky planet is its composition. Unlike the giant planets, which are composed primarily of hydrogen and helium gas, rocky planets are made of heavier elements, particularly oxygen, silicon, magnesium, and iron. These elements combine to form the silicate minerals that make up rocky mantles and the metallic iron that sinks to form dense cores. The relative proportions of these materials determine the overall density and internal structure of the planet. Rocky planets form in the inner regions of protoplanetary disks, where temperatures are too high for water ice and other volatile compounds to exist as solids. In these warm zones, only refractory materials, Those with high melting and vaporization temperatures can condense from the disk gas and contribute to planet building. This limitation on available materials means that rocky planets are inherently smaller than their giant counterparts, as there is simply less solid material available in the inner disk. The internal structure of a typical rocky planet consists of several distinct layers. At the center lies a dense core composed primarily of iron, often alloyed with nickel, and smaller amounts of lighter elements. Surrounding the core is a thick mantle made of silicate rocks, materials composed of silicon and oxygen bonded with metals like magnesium and iron. At the surface, a thin crust of lower density silicates forms the outermost solid layer. This layered structure arises from differentiation, the process by which denser materials sink toward the center, while lighter materials rise toward the surface. Differentiation occurs when a rocky planet is hot enough for its interior to behave as a fluid, allowing materials to separate according to their densities. The heat required for differentiation can come from several sources. The energy released by accretion, as countless smaller bodies collide and merge to form the growing planet, provides substantial heating. Radioactive decay of elements like uranium, thorium, and potassium generates heat over longer timescales. Giant impacts during the late stages of planet formation can deliver enough energy to completely melt a planet, ensuring thorough differentiation. The size of a rocky planet's core relative to its overall size depends on the planet's formation history and the composition of the material from which it formed. Mercury, the innermost planet in our solar system, has an unusually large core that comprises about 85% of the planet's radius, suggesting that Mercury may have lost a significant portion of its original mantle through a giant impact or through vaporization by the young sun. In contrast, Mars has a relatively small core, comprising only about half of the planet's radius, reflecting a lower overall iron content. The presence or absence of a magnetic field is closely tied to a rocky planet's internal structure and thermal evolution. Magnetic fields are generated by the dynamo effect, which requires a liquid metallic core with convective motions driven by heat escaping from the planet's interior. Earth possesses a strong magnetic field because its outer core remains liquid and vigorously convecting. Mars, despite having a metallic core, has lost its global magnetic field, likely because its smaller size allowed it to cool more rapidly, causing its core to solidify or at least to cease convecting. Magnetic fields play crucial roles in determining the habitability of rocky planets. A strong magnetic field deflects charged particles from the solar wind, preventing them from stripping away the planet's atmosphere. Mars, lacking a global magnetic field for most of its history, has lost much of its original atmosphere to space, contributing to its current cold and dry conditions. Understanding the factors that determine whether a rocky planet maintains a magnetic field is therefore essential for assessing the potential habitability of distant worlds. The surfaces of rocky planets are shaped by a combination of internal and external processes. Internal processes include volcanism, driven by heat escaping from the planet's interior, and tectonics, the movement and deformation of crustal plates. External processes include impact cratering, caused by collisions with asteroids and comets, and erosion by wind, water, or ice. The relative importance of these processes varies from planet to planet, depending on factors like size, composition, atmospheric properties, and distance from the Sun. Volcanism is one of the most important geological processes on rocky planets. When heat from the interior causes mantle rock to melt, the resulting magma can rise toward the surface and erupt, building volcanic mountains and flooding low-lying areas with lava flows. Volcanic activity releases gases trapped in the planet's interior, contributing to the formation and evolution of atmospheres. On Earth, volcanic outgassing has played a crucial role in maintaining atmospheric composition over billions of years, replenishing gases lost to space and chemical reactions. The style of volcanism varies depending on the properties of the magma and the planet's gravity and atmospheric pressure. On Earth, volcanism produces a wide variety of landforms, from gentle shield volcanoes built by fluid basaltic lava to explosive stratovolcanoes that erupt viscous, gas-rich magma. On Venus, the high surface pressure suppresses explosive eruptions, leading to a predominance of effusive volcanism that has resurfaced much of the planet with basaltic lava flows. On Mars, lower gravity allows volcanic structures to grow to enormous sizes, as exemplified by Olympus Mons, the largest known volcano in the solar system. Plate tectonics, the process by which a planet's outer shell is divided into rigid plates that move relative to one another, is a defining characteristic of Earth's geology. The movement of tectonic plates creates mountain ranges where plates collide, ocean basins where plates spread apart, and volcanic arcs where one plate slides beneath another. Plate tectonics also plays a crucial role in Earth's carbon cycle, recycling carbon dioxide between the atmosphere and the planet's interior and helping to regulate surface temperatures over geological timescales. Earth appears to be unique among the rocky planets of our solar system in possessing active plate tectonics. Venus, despite being similar in size to Earth, shows no evidence of plate tectonics, instead displaying a style of volcanism and tectonics that resurfaces the planet episodically through massive volcanic outpourings. Mars, being smaller than Earth, has cooled more rapidly and developed a thick, rigid lithosphere that prevents plate motion. Mercury, smaller still, shows evidence only of global contraction as its interior cooled and shrank. The question of why Earth has plate tectonics while other rocky planets do not remains an active area of research. Several factors likely contribute, including Earth's size, composition, water content, and thermal history. Water appears to play a particularly important role as it weakens rocks and lubricates fault zones, facilitating the subduction of oceanic plates beneath continental plates. The presence of liquid water on Earth's surface may therefore be not only a consequence of habitability, but also a cause of the geological activity that helps maintain habitable conditions. Impact cratering is a universal process that affects all rocky surfaces in the solar system. When an asteroid or comet strikes a planetary surface at high velocity, it releases enormous energy, excavating a crater and ejecting debris across the surrounding terrain. The size of the resulting crater depends on the size and velocity of the impactor and the properties of the target surface. Small impacts produce simple bowl-shaped craters, while larger impacts create complex craters with central peaks, terraced walls, and surrounding ejector blankets. The surfaces of rocky planets preserve records of impact cratering extending back billions of years. By counting craters and measuring their sizes, planetary scientists can estimate the ages of different surface regions. Heavily cratered surfaces are generally older, having accumulated impacts over longer periods, while lightly cratered surfaces are younger, having been resurfaced by geological activity more recently. This technique, called crater counting, has been essential for reconstructing the geological histories of planets and moons throughout the solar system. Atmospheres represent another crucial aspect of rocky planet diversity. An atmosphere is a layer of gas bound to a planet by gravity, and the presence, composition, and density of an atmosphere profoundly affect surface conditions. Atmospheres moderate temperature extremes, distribute heat from dayside to nightside, protect surfaces from harmful radiation and small impactors, and can enable the existence of liquid water through the greenhouse effect. The fate of a rocky planet's atmosphere depends on a complex interplay of factors, including the planet's mass, temperature, magnetic field, and geological activity. Earth's atmosphere is composed primarily of nitrogen and oxygen, with smaller amounts of water vapor, argon, carbon dioxide, and trace gases. This composition is unique in our solar system and reflects billions of years of geological and biological evolution. Oxygen, which makes up about 21% of Earth's atmosphere, is almost entirely the product of photosynthesis by plants, algae, and cyanobacteria. Without life, Earth's atmosphere would likely resemble those of Venus and Mars, dominated by carbon dioxide, with little or no free oxygen. Venus possesses a massive atmosphere composed almost entirely of carbon dioxide, with surface pressures roughly 90 times those on Earth. This dense atmosphere creates an extreme greenhouse effect that raises surface temperatures to approximately 900 degrees Fahrenheit, making Venus the hottest planet in the solar system despite being farther from the Sun than Mercury. The thick clouds of sulfuric acid that shroud Venus reflect much of the incoming sunlight, but enough energy penetrates to maintain the scorching surface conditions. Mars, in contrast, has only a thin wisp of an atmosphere, with surface pressures less than 1% of those on Earth. This tenuous atmosphere, also composed primarily of carbon dioxide, provides little greenhouse warming and minimal protection from solar radiation. The low atmospheric pressure means that liquid water cannot exist stably on the Martian surface under current conditions, though evidence suggests that Mars once possessed a thicker atmosphere and flowing water in its distant past. The diversity of atmospheres among rocky planets raises important questions about atmospheric evolution. Why did Venus develop such a massive atmosphere while Mars lost most of its original atmosphere to space? The answers involve a combination of factors, including planetary size, distance from the Sun, magnetic field strength, and geological activity. Understanding these factors is essential for predicting the atmospheric properties of rocky exoplanets and assessing their potential habitability. Water, in its various forms, is perhaps the most important substance for determining the habitability of rocky planets. Liquid water is essential for all known forms of life, serving as the medium in which biochemical reactions occur. The presence of liquid water on a planetary surface requires temperatures and pressures within a relatively narrow range, conditions that depend on both the planet's distance from its star and the properties of its atmosphere. Earth's position within the Sun's habitable zone, combined with its moderate greenhouse effect, has allowed liquid water to persist on its surface for billions of years. The search for water on other rocky planets has been a major focus of planetary exploration. Mars shows abundant evidence of past water activity, including ancient river valleys, lake beds, and mineral deposits that form in the presence of water. Current Mars possesses water ice at its polar caps and likely in subsurface deposits, but liquid water cannot exist stably under present conditions. Venus may have had liquid water early in its history, but runaway greenhouse warming long ago vaporized any surface water and allowed it to escape to space. As we consider the diversity of rocky worlds, it becomes clear that Earth represents just one possibility among many. Rocky planets can be larger or smaller than Earth, closer to or farther from their stars, with thicker or thinner atmospheres, and with varying degrees of geological activity. Some rocky planets may be covered entirely by oceans, while others may be completely desiccated. Some may have active plate tectonics, while others may be geologically dead. This diversity offers both challenges and opportunities for the search for life beyond Earth. Let these thoughts of rocky worlds settle gently in your mind as you continue to relax. From the scorched plains of Mercury to the frozen deserts of Mars, from the volcanic hellscape of Venus to the blue-green oasis of Earth, rocky planets display an astonishing range of conditions and environments. Each of these worlds has its own story, shaped by the particular circumstances of its formation and evolution. Beyond the warm inner regions of planetary systems, where rocky worlds bask in the light of their parent stars, lie the cold outer reaches, where a different class of planet reigns supreme. The giant planets, massive worlds composed primarily of hydrogen, helium, and heavier volatile compounds, dominate the outer regions of our solar system and many others throughout the galaxy. These colossal worlds, with their swirling atmospheres, extensive ring systems, and families of moons, represent some of the most spectacular objects in the universe. As you settle deeper into relaxation, let us journey to these distant giants and explore their wonders. Giant planets are fundamentally different from rocky planets in almost every respect. While rocky planets are built from the refractory materials that could survive in the warm inner disk, giant planets formed in the cold outer regions, where volatile compounds like water, ammonia, and methane could condense as ices. This abundance of solid material beyond the snowline allowed giant planet cores to grow large enough to capture massive envelopes of hydrogen and helium gas, transforming them into the enormous worlds we observe today. The giant planets of our solar system divide naturally into two categories: the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. Gas giants are dominated by hydrogen and helium, with compositions similar to that of the Sun itself. Ice giants, while still possessing substantial hydrogen and helium envelopes, contain higher proportions of heavier elements, particularly water, ammonia, and methane. This compositional difference reflects different formation histories and different degrees of gas accretion during the planet-building process. Jupiter, the largest planet in our solar system, serves as the archetype for gas giant planets throughout the universe. With a mass of approximately 318 Earth masses and a diameter of about 86,881 miles, Jupiter contains more than twice the mass of all other planets in our solar system combined. Despite its enormous size, Jupiter is composed almost entirely of hydrogen and helium, the two lightest elements in the universe. If you could somehow find a bathtub large enough to hold it, Saturn would float, though Jupiter would sink, being slightly denser than water. The internal structure of Jupiter remains a subject of active research, but current models suggest a layered configuration quite different from that of rocky planets. At the very centre may lie a dense core of heavier elements, perhaps 10 to 20 times the mass of Earth, representing the original seed around which the planet formed. Surrounding this core is a vast envelope of hydrogen and helium that extends nearly to the visible cloud tops. However, the conditions within this envelope vary dramatically with depth. In the outer regions of Jupiter's envelope, hydrogen exists as a molecular gas similar to the hydrogen in Earth's atmosphere. As depth increases, however, pressure and temperature rise steadily. At depths corresponding to pressures of about 2 million Earth atmospheres, hydrogen undergoes a remarkable transformation, becoming metallic. In this exotic state, hydrogen atoms are squeezed so tightly together that their electrons become free to move throughout the material, allowing it to conduct electricity like a metal. Jupiter's metallic hydrogen layer is believed to generate the planet's powerful magnetic field through dynamo action. Jupiter's visible appearance is dominated by alternating bands of light and dark clouds that circle the planet parallel to its equator. The lighter bands, called zones, represent regions of rising atmosphere where gases cool and condense to form high-altitude clouds of ammonia ice. The darker bands, called belts, represent regions of sinking atmosphere where warmer temperatures prevent cloud formation, allowing us to see deeper into the atmosphere. The boundary between zones and belts is marked by powerful jet streams, with wind speeds reaching hundreds of miles per hour. The most famous feature in Jupiter's atmosphere is the Great Red Spot, an enormous anticyclonic storm that has been observed for at least 350 years and possibly much longer. This colossal vortex is large enough to swallow Earth with room to spare, though recent observations indicate that it has been gradually shrinking over the past century. The Great Red Spot rotates counterclockwise with a period of about 6 days, drawing its energy from the smaller storms and atmospheric disturbances that it absorbs. The distinctive red colour is believed to result from complex organic molecules created when solar ultraviolet light interacts with chemicals in the upper atmosphere. Jupiter possesses the most extensive moon system of any planet in our solar system, with 95 confirmed satellites as of recent counts. The 4 largest moons, discovered by Galileo Galilei in 1610, are called the Galilean moons and are worlds of considerable interest in their own right. These 4 moons, Io, Europa, Ganymede and Callisto, are each unique and fascinating, offering insights into the diversity of worlds that can exist around giant planets. Io, the innermost Galilean moon, is the most volcanically active body in the solar system. Despite being only slightly larger than Earth's moon, Io possesses hundreds of active volcanoes that continuously resurface the moon with sulfur and silicate lavas. This intense volcanic activity is powered by tidal heating, the frictional dissipation of energy as Io's interior is flexed by Jupiter's enormous gravity. Io's elliptical orbit, maintained by gravitational resonances with Europa and Ganymede, ensures that tidal forces vary throughout each orbit, continuously pumping energy into the moon's interior. Europa, the second Galilean moon, presents a dramatically different face. Its surface is covered by a shell of water ice, crisscrossed by a complex network of ridges, fractures, and chaotic terrain. Beneath this icy shell lies a global ocean of liquid water, kept liquid by tidal heating similar to that which drives Io's volcanism. This subsurface ocean contains more water than all of Earth's oceans combined and represents one of the most promising environments for extraterrestrial life in our solar system. Future missions aim to explore Europa's ocean, searching for signs of life in its dark, salty waters. Ganymede, the largest moon in the solar system, exceeds even the planet Mercury in diameter. This giant moon possesses a differentiated interior with a metallic core, a rocky mantle, and an outer shell of ice. Ganymede is the only moon known to generate its own magnetic field, indicating that its metallic core remains at least partially liquid and convecting. The moon's surface displays 2 distinct terrain types: ancient, heavily cratered dark regions, and younger, grooved, bright terrain that may have formed through tectonic processes. Callisto, the outermost Galilean moon, presents yet another variation on the theme of icy worlds. Its surface is among the most heavily cratered in the solar system, indicating that it has remained geologically inactive for billions of years. Unlike Ganymede, Callisto appears to be only partially differentiated, with ice and rock mixed throughout its interior rather than separated into distinct layers. This incomplete differentiation may reflect a gentler formation history with less intense heating. Saturn, the second largest planet in our solar system, shares many characteristics with Jupiter but possesses its own unique features that make it one of the most beautiful objects in the cosmos. With a mass of approximately 95 Earth masses and a diameter of about 72,366 miles, Saturn is substantially smaller than Jupiter, but still enormous by any terrestrial standard. Saturn's lower density, only about 70% that of water, reflects a higher proportion of hydrogen and helium relative to heavier elements. The feature that makes Saturn instantly recognizable is its magnificent ring system. While all 4 giant planets possess rings, Saturn's rings are by far the most extensive and spectacular. They extend outward from about 4,000 miles above Saturn's cloud tops to nearly 300,000 miles from the planet's centre, yet they are remarkably thin, typically measuring only about 30 feet in thickness. If you could shrink Saturn's rings to the size of a compact disk, they would be thinner than a razor blade. Saturn's rings are composed primarily of water ice particles, ranging in size from tiny grains to house-sized chunks. The rings are divided into several distinct regions separated by gaps, the most prominent of which is the Cassini division, a 2,900-mile wide gap visible through small telescopes from Earth. These gaps are created by gravitational resonances with Saturn's moons, which clear out particles from certain orbital distances. The intricate structure of the rings, with thousands of individual ringlets and waves, reflect the complex gravitational environment around Saturn. The origin of Saturn's rings remains a subject of debate among planetary scientists. One hypothesis suggests that the rings formed from the debris of a moon or comet that ventured too close to Saturn and was torn apart by tidal forces. Another possibility is that the rings are primordial, dating back to the formation of the Saturn system itself. Data from the Cassini mission, which orbited Saturn from 2004 to 2017, suggests that the rings may be relatively young, perhaps only 100 million years old, though this conclusion remains controversial. Saturn's moon system rivals Jupiter's in complexity, with 146 confirmed satellites. The largest, Titan, is the second largest moon in the solar system, and the only moon known to possess a dense atmosphere. Titan's atmosphere is composed primarily of nitrogen, with methane and other hydrocarbons as minor constituents. Surface temperatures of around -290 degrees Fahrenheit allow methane to exist as a liquid, and Titan possesses lakes and seas of liquid hydrocarbons near its poles. The Huygens probe, which landed on Titan in 2005, revealed a landscape shaped by methane rain, rivers, and lakes, eerily similar to Earth's water cycle, but operating at much colder temperatures. Enceladus, a small icy moon only about 310 miles in diameter, has emerged as one of the most intriguing objects in the solar system. Despite its small size, Enceladus is geologically active, venting plumes of water vapor and ice particles from fractures near its south pole. These plumes originate from a subsurface ocean of liquid water, heated by tidal interactions with Saturn. Analysis of the plume material by the Cassini spacecraft revealed the presence of organic molecules and molecular hydrogen, suggesting that hydrothermal activity may be occurring on Enceladus's ocean floor. Like Europa, Enceladus represents a potential habitat for extraterrestrial life. Uranus and Neptune, the ice giants of our solar system, represent a distinct category of giant planet. These worlds are substantially smaller than Jupiter and Saturn, with masses of about 14.5 and 17 Earth masses respectively, but they are still far larger than any rocky planet. Their compositions differ significantly from the gas giants, with higher proportions of heavier elements, including water, ammonia, and methane. The term ice giant refers not to frozen surfaces, but to the abundance of these volatile compounds in the planet's interiors. Uranus, the 7th planet from the Sun, possesses one of the most unusual characteristics of any planet, its extreme axial tilt of approximately 98 degrees. While most planets rotate with their axes roughly perpendicular to their orbital planes, Uranus essentially rolls around the Sun on its side. This extreme tilt is believed to result from one or more giant impacts early in the planet's history. The consequences for Uranus's climate are profound, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness during the planet's 84-year orbit. Despite receiving very little solar energy at its great distance from the Sun, Uranus's atmosphere displays subtle banding and occasional storm activity. The planet's distinctive blue-green colour results from methane in its atmosphere, which absorbs red light and reflects blue. Uranus possesses a system of narrow dark rings that were discovered in 1977 when astronomers observed the planet passing in front of a distant star. These rings are composed of dark particles, possibly organic compounds or radiation-darkened ice, and are much less reflective than Saturn's brilliant ice rings. Uranus is accompanied by 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, are icy worlds with surfaces shaped by impacts, and in some cases, geological activity. Miranda is particularly notable for its chaotic surface, which displays enormous canyons, terraced layers, and jumbled terrain that suggest a complex and violent history. Some scientists have proposed that Miranda was shattered by a giant impact and subsequently reassembled, though other explanations involving tidal heating and cryovolcanism have also been suggested. Neptune, the 8th and outermost planet in our solar system, orbits at an average distance of approximately 2.8 billion miles from the Sun. At this vast distance, Neptune receives only about 1,000th the solar energy that Earth does, yet its atmosphere is surprisingly dynamic and active. Neptune possesses the fastest winds measured on any planet, with speeds reaching over 1,200 miles per hour in some regions. This vigorous atmospheric activity, despite minimal solar heating, suggests that Neptune possesses a significant internal heat source that drives its weather patterns. Neptune's deep blue colour, more vivid than Uranus's blue-green hue, also results from methane absorption of red light, though the exact cause of the colour difference between the two ice giants remains uncertain. When Voyager 2 flew past Neptune in 1989, it observed a large dark storm called the Great Dark Spot, reminiscent of Jupiter's Great Red Spot. However, subsequent observations by the Hubble Space Telescope revealed that the Great Dark Spot had disappeared, only to be replaced by new dark spots in different locations. Neptune's storms appear to be more transient than Jupiter's long-lived features. Neptune possesses a system of faint rings, discovered during the Voyager 2 flyby. These rings are composed of dark particles similar to those in Uranus's rings, and include several distinct ring arcs, regions where ring material is concentrated into clumps, rather than distributed uniformly around the planet. The ring arcs were initially puzzling, as gravitational dynamics should cause ring material to spread out evenly over time. The gravitational influence of Neptune's small inner moons appears to confine the ring arcs, preventing them from dispersing. Neptune's largest moon, Triton, is one of the most intriguing objects in the outer solar system. With a diameter of about 1,680 miles, Triton is the 7th largest moon in the solar system, and the only large moon that orbits its planet in a retrograde direction, meaning it moves opposite to Neptune's rotation. This retrograde orbit strongly suggests that Triton did not form alongside Neptune, but was instead captured from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Triton's surface is among the coldest in the solar system, with temperatures around negative 391 degrees Fahrenheit. Despite these frigid conditions, Triton displays evidence of geological activity. The Voyager 2 spacecraft observed active geysers erupting from Triton's surface, shooting plumes of nitrogen gas and dark particles several miles into the thin atmosphere. These geysers may be powered by solar heating of subsurface nitrogen ice, which vaporizes and erupts through cracks in the surface. Triton's young, sparsely cratered surface suggests that geological processes have resurfaced much of the Moon relatively recently in geological terms. Triton's captured orbit has profound implications for its future. Tidal interactions with Neptune are gradually causing Triton's orbit to decay, bringing the Moon slowly closer to the planet. In the distant future, perhaps 1 billion years from now, Triton will cross Neptune's Roche limit, the distance within which tidal forces exceed the Moon's own gravity. At that point, Triton will be torn apart, potentially creating a spectacular ring system around Neptune that could rival or exceed Saturn's rings in grandeur. The giant planets of our solar system, diverse as they are, represent only a small sample of the giant planet population throughout the galaxy. The giant planets we know best, Jupiter, Saturn, Uranus, and Neptune, are merely our local examples of a much broader and more diverse population. As you continue to drift and relax, let the images of these magnificent worlds float through your mind. Picture Jupiter's swirling bands and ancient storms, Saturn's ethereal rings catching the distant sunlight, Uranus rolling along its tilted orbit, and Neptune's deep blue atmosphere stirred by invisible winds. These giant worlds, so different from our small rocky Earth, remind us of the incredible variety that exists within planetary systems. They are worlds of superlatives, of extremes, of conditions utterly unlike anything we experience in our daily lives. Yet they are part of our cosmic family, fellow travellers around our shared sun. For most of human history, the planets of our own solar system were the only worlds we knew. The question of whether other stars possessed their own planetary systems remained firmly in the realm of speculation and philosophy, beyond the reach of observational science. All of that changed in the final years of the 20th century, when astronomers developed techniques sensitive enough to detect planets orbiting distant stars. The discovery of these exoplanets, as they came to be called, revolutionized our understanding of planetary systems and opened entirely new chapters in the story of worlds beyond our own. As you rest peacefully, let us explore this remarkable revolution and the methods that made it possible. The search for exoplanets faced enormous challenges from the outset. Planets are small, dim objects that shine only by reflected starlight, while stars are brilliant sources of light that outshine any accompanying planets by factors of millions to billions. Trying to see an exoplanet directly is often compared to trying to spot a firefly next to a searchlight from thousands of miles away. For this reason, the first successful exoplanet detections relied not on seeing the planets directly, but on detecting their subtle gravitational and geometric effects on their host stars. The radial velocity method, also known as Doppler spectroscopy, was the first technique to yield confirmed detections of exoplanets around Sun-like stars. This method exploits the fact that a planet does not simply orbit its star. Rather, both the planet and the star orbit their common centre of mass. For a massive planet, this causes the star to wobble slightly, moving toward and away from Earth as the planet completes its orbit. This motion produces tiny shifts in the wavelengths of light from the star, shifts that can be measured using precise spectrographs. The radial velocity method is most sensitive to massive planets orbiting close to their stars, as these produce the largest stellar wobbles. It was therefore no coincidence that the first exoplanet discovered around a Sun-like star was a massive world in a very tight orbit. In 1995, Swiss astronomers Michel Mayer and Didier Queloz announced the detection of a planet orbiting the star 51 Pegasi, located about 50 light-years from Earth. This planet, designated 51 Pegasi b, had a mass at least half that of Jupiter, but orbited its star in just 4.2 days, placing it far closer to its star than Mercury is to our Sun. The discovery of 51 Pegasi b was shocking to planetary scientists, who had expected other planetary systems to resemble our own, with small rocky planets close to the star and giant planets far away. Here was a Jupiter-mass planet orbiting closer to its star than any planet in our solar system, in a region where conventional theories said giant planets could not form. This unexpected finding, soon confirmed by other teams and followed by additional discoveries of similar objects, forced a fundamental rethinking of planet formation theories and introduced the concept of planetary migration to explain how giant planets could end up so close to their stars. Throughout the late 1990s and early 2000s, the radial velocity method continued to yield new exoplanet discoveries at an accelerating pace. Improvements in spectrograph precision allowed the detection of smaller stellar wobbles corresponding to less massive planets, or planets in wider orbits. By the mid-2000s, the known exoplanet population had grown to include hundreds of worlds, revealing a diversity of planetary systems far greater than anyone had anticipated. While the radial velocity method was accumulating discoveries, another technique was being developed that would eventually surpass it in productivity. The transit method detects exoplanets by observing the slight dimming of a star's light when a planet passes in front of it, blocking a small fraction of the starlight from reaching Earth. The amount of dimming depends on the relative sizes of the planet and star, with larger planets blocking more light and producing deeper transits. The transit method has several advantages over the radial velocity method. It can survey many stars simultaneously, making it well suited for space-based observatories that can monitor thousands or millions of stars at once. It provides direct information about the planet's size, which the radial velocity method cannot determine. And when combined with radial velocity measurements, transit observations allow astronomers to calculate the planet's density, providing clues about its composition. The transit method also has limitations. It can only detect planets whose orbits happen to be aligned so that they pass between their star and Earth, a geometric requirement that is satisfied for only a small fraction of planetary systems. For a planet in an Earth-like orbit around a Sun-like star, the probability of the correct alignment is less than 1%. This means that transit surveys must observe many stars to find a significant number of transiting planets. The first confirmed transiting exoplanet was HD 294558b, detected in 1999. This hot Jupiter, previously discovered by the radial velocity method, was observed to transit its star, causing a 1.5% dimming of the starlight every 3.5 days. The transit observations confirmed the planet's existence and allowed astronomers to determine its size, revealing that it was larger than expected for its mass, likely due to heating from its nearby star. The true potential of the transit method was realized with the launch of dedicated space telescopes designed to search for transiting exoplanets. The first of these was CoRoT, a French-led mission launched in 2006 that discovered several dozen transiting planets during its operational lifetime. But the mission that truly transformed exoplanet science was NASA's Kepler Space Telescope, launched in 2009. Kepler was designed to answer a fundamental question: how common are Earth-sized planets in Earth-like orbits around Sun-like stars? To address this question, Kepler stared continuously at a single patch of sky containing about 150,000 stars, monitoring their brightness with unprecedented precision. Over its 4-year primary mission, Kepler detected thousands of candidate transiting planets, revolutionizing our understanding of planetary system demographics. The Kepler mission's discoveries were remarkable in both quantity and quality. Kepler found planets of all sizes, from smaller than Earth to larger than Jupiter. It discovered planets in orbits ranging from less than a day to more than a year. It found planets orbiting single stars and planets orbiting binary star systems. It revealed that multi-planet systems are common, with many stars hosting 2, 3, or even more detectable planets. By the time Kepler's primary mission ended in 2013, it had identified over 2,600 confirmed exoplanets and thousands of additional candidates awaiting confirmation. One of Kepler's most important findings was that small planets are far more common than large ones. While the first exoplanet discoveries had been dominated by giant planets, which are easiest to detect, Kepler revealed that Earth-sized and super-Earth-sized planets vastly outnumber Jupiter-sized worlds. Statistical analyses of Kepler data suggest that virtually every star in the galaxy has at least one planet, and that rocky planets in the habitable zones of their stars may number in the billions within our galaxy alone. Kepler also discovered entirely new categories of planets that have no counterparts in our solar system. Super-Earths, planets with masses between Earth and Neptune, turned out to be among the most common types of planets in the galaxy, yet our solar system contains none. Mini-Neptunes, planets slightly smaller than Neptune with thick gaseous envelopes, are similarly abundant. The prevalence of these intermediate-sized planets raises important questions about planet formation and evolution that scientists are still working to answer. Following the end of Kepler's primary mission, the telescope was repurposed for an extended mission called K2, which observed different regions of the sky for shorter periods. K2 continued to discover exoplanets until the spacecraft exhausted its fuel in 2018. By that time, Kepler and K2 together had discovered over 2,700 confirmed exoplanets, more than any other telescope or survey. The successor to Kepler is NASA's Transiting Exoplanets Survey satellite, or TESS, launched in 2018. While Kepler stared at a single patch of sky, TESS surveys nearly the entire sky, focusing on the nearest and brightest stars. This strategy is designed to find exoplanets that are well suited for follow-up observations, including atmospheric characterization with other telescopes. TESS has already discovered thousands of exoplanet candidates, including many orbiting nearby stars that will be prime targets for future study. Beyond the radial velocity and transit methods, several other techniques have contributed to exoplanet discoveries. Direct imaging involves blocking the light from a star and photographing the planets orbiting it. This technique is most effective for young massive planets in wide orbits, which are brightest in infrared light. Direct imaging has revealed several spectacular planetary systems, including HR 8799, which hosts 4 giant planets that have been photographed multiple times as they orbit their star. Gravitational microlensing detects planets through their gravitational effects on light from more distant background stars. When a star with a planet passes in front of a more distant star, the gravity of the foreground system bends and magnifies the light from the background star. The presence of a planet creates additional features in the magnification pattern that can reveal the planet's mass and orbital distance. Microlensing is sensitive to planets that are difficult to detect by other methods, including free-floating planets that do not orbit any star. Astrometry involves measuring the precise positions of stars over time, looking for the tiny wobbles caused by orbiting planets. While conceptually, Similar to the radial velocity method, astrometry measures motion across the sky rather than toward and away from Earth. Astrometry has been challenging from the ground due to atmospheric distortions, but space-based observatories like Gaia are beginning to detect exoplanets through this technique. The combination of these various detection methods has revealed an exoplanet population of remarkable diversity. As of late 2024, astronomers have confirmed the existence of over 5,700 exoplanets, with thousands more candidates awaiting confirmation. These planets orbit stars of all types, from tiny red dwarfs to massive blue giants. They range in size from smaller than Earth to larger than Jupiter. They occupy orbits ranging from scorchingly close to their stars to frigidly distant. The diversity of known exoplanets far exceeds the diversity within our own solar system, challenging our theories and expanding our imagination. As you rest and let these discoveries wash over you, consider the profound implications of the exoplanet revolution. We now know that planets are not rare accidents, but common outcomes of star formation. We know that planetary systems come in an astonishing variety of configurations, many quite different from our own. We know that rocky planets exist in the habitable zones of other stars, places where liquid water might exist on the surface. The universe, it turns out, is filled with worlds, and the story of planetary systems extends far beyond our own small corner of the cosmos. The exoplanets discovered over the past 3 decades have revealed a universe far stranger and more varied than anyone imagined. While our own solar system contains a tidy arrangement of rocky inner planets and giant outer planets, other planetary systems display configurations that seem almost impossible by comparison. Hot Jupiters roast in the glare of their parent stars. Super-Earths and mini-Neptunes occupy size ranges absent from our solar system. Planets orbit binary stars, circling 2 suns like the fictional Tatooine from Star Wars. Some planets wander through the galaxy alone, unbound to any star. As you continue to relax, let us explore this menagerie of strange new worlds and marvel at the creativity of cosmic planet building. Hot Jupiters were the first type of exoplanet to be discovered in significant numbers, and they remain among the most dramatic examples of planetary diversity. These massive worlds, comparable in size to Jupiter, orbit their stars at distances far smaller than Mercury's orbit around our Sun. A typical hot Jupiter completes one orbit in just a few days, racing around its star at tremendous speed while being heated to temperatures of thousands of degrees. The existence of hot Jupiters posed an immediate challenge to theories of planet formation. Giant planets are thought to form beyond the snowline, where temperatures are cold enough for water ice to condense and contribute to planet building. The snowline in a typical protoplanetary disk lies several astronomical units from the central star, far beyond the orbits where hot Jupiters are found. How, then, did these massive worlds end up so close to their stars? The answer lies in planetary migration, the process by which planets change their orbital distances over time. Giant planets forming in the outer disk can interact gravitationally with the disk material, exchanging angular momentum and spiraling inward toward the star. This migration can transport a Jupiter-mass planet from beyond the snowline to within a few stellar radii of its host star. The migration must stop before the planet falls into the star, perhaps when the inner disk is cleared by stellar radiation, or when the disk itself disperses. Hot Jupiters experience extreme conditions unlike anything in our solar system. Their dayside temperatures can exceed 2,000 degrees Fahrenheit, hot enough to vaporize rock and metal. Many hot Jupiters are tidally locked to their stars, meaning one hemisphere permanently faces the star while the other remains in eternal darkness. This creates enormous temperature contrasts between the day and night sides, driving powerful atmospheric circulation that attempts to redistribute heat around the planet. The atmospheres of hot Jupiters have been studied in considerable detail using transit spectroscopy, a technique that analyzes starlight filtering through a planet's atmosphere during transit. These observations have revealed the presence of various molecules, including water vapor, carbon monoxide, and even exotic species like titanium oxide and vanadium oxide in the hottest examples. Some hot Jupiters appear to have clouds or hazes that obscure their lower atmospheres, while others display clear skies that allow deeper probing. One of the most extreme hot Jupiters known is Kelt 9b, which orbits a hot luminous star and reaches dayside temperatures of over 7,800 degrees Fahrenheit, hotter than many stars. At these temperatures, molecules are torn apart into their constituent atoms, and the planet's atmosphere contains atomic hydrogen, iron, and other metals in gaseous form. Kelt 9b is slowly evaporating, losing mass to space as its atmosphere is stripped away by the intense stellar radiation. While hot Jupiters captured early attention due to their ease of detection, they are actually quite rare, occurring around only about 1% of Sun-like stars. Far more common are the super-Earths and mini-Neptunes, planets with sizes between Earth and Neptune that have no counterparts in our solar system. These intermediate-sized worlds appear to be the most abundant type of planet in the galaxy, yet their nature and origins remain subjects of active research. Super-Earths are typically defined as planets with masses between about 1 and 10 Earth masses, or radii between about 1 and 1.75 Earth radii. The term suggests rocky planets larger than Earth, and indeed some super-Earths may be scaled-up versions of our own world, with iron cores, silicate mantles, and thin atmospheres. However, the super-Earth category likely includes a diverse range of compositions, from dense iron-rich worlds to water-rich ocean planets to planets with thick hydrogen envelopes. Mini-Neptunes, sometimes called sub-Neptunes, are planets with radii between about 1.75 and 3.5 Earth radii. These worlds are thought to possess substantial gaseous envelopes surrounding rocky or icy cores, making them more similar to Neptune than to Earth despite their smaller sizes. The boundary between super-Earths and mini-Neptunes is not sharp, and distinguishing between a large rocky planet and a small gaseous planet requires measurements of both size and mass to determine density. Intriguingly, there appears to be a gap in the size distribution of small exoplanets, with relatively few planets having radii between about 1.5 and 2 Earth radii. This radius gap, sometimes called the Fulton Gap after the astronomer who characterized it, may reflect the effects of atmospheric loss. Planets slightly larger than Earth may lose their primordial hydrogen envelopes to stellar radiation, shrinking down to bare rocky cores. Planets that start with more massive envelopes may retain enough gas to remain as mini-Neptunes. The radius gap thus represents a dividing line between planets that kept their atmospheres and those that lost them. Some of the most intriguing exoplanets are those that orbit within the habitable zones of their stars, the regions where temperatures might allow liquid water to exist on a planetary surface. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting a small red dwarf star, with 3 or 4 of them located within the habitable zone. This remarkable system, located about 40 light-years from Earth, represents one of the best opportunities to study potentially habitable worlds around other stars. The TRAPPIST-1 planets are locked in a chain of orbital resonances, with their orbital periods forming simple integer ratios. This resonant configuration suggests that the planets migrated inward through the protoplanetary disk, becoming trapped in resonances as they approach the star. The planets are so close together that from the surface of one, the others would appear as large as or larger than the Moon appears from Earth, creating spectacular views in alien skies. Circumbinary planets, worlds that orbit two stars rather than one, represent another category of exotic exoplanets. The first confirmed circumbinary planet, Kepler-16b, was announced in 2011 and immediately drew comparisons to Tatooine, the fictional homeworld of Luke Skywalker in Star Wars. Kepler-16b is a Saturn-sized gas giant that orbits both stars of a binary system, experiencing two sunrises and two sunsets as the stars move through its sky. The existence of circumbinary planets was once considered unlikely, as the gravitational perturbations from two stars were thought to prevent planet formation or destabilize planetary orbits. The discovery of Kepler-16b and subsequent circumbinary planets demonstrated that nature is more creative than theorists had assumed. Circumbinary planets must form in disks that surround both stars, and they must avoid regions of orbital instability close to the binary. The planets that survive occupy orbits far enough from the binary to remain stable over billions of years. Rogue planets, also called free-floating planets or nomad planets, are worlds that drift through interstellar space without being bound to any star. These lonely wanderers may have formed around stars and been ejected through gravitational interactions with other planets, or they may have formed independently in interstellar clouds through processes similar to star formation. Estimates suggest that rogue planets may be as common as stars in the galaxy, meaning billions of these dark worlds may be drifting through the Milky Way. Detecting rogue planets is challenging because they emit no light of their own and do not transit any star. The primary detection method is gravitational microlensing, which can reveal the presence of a massive object through its gravitational effects on light from background stars. Microlensing surveys have detected several candidate rogue planets, including some with masses similar to Earth. Future surveys may reveal the true abundance of these interstellar wanderers. Some exoplanets orbit stars in extreme environments that seem hostile to planet formation. Planets have been found orbiting pulsars, the rapidly spinning remnants of massive stars that exploded as supernovae. The first exoplanets ever discovered, announced in 1992, were found orbiting the pulsar PSR B+12. These planets may have formed from a debris left over after the supernova explosion, or they may be the remnants of larger bodies that survived the stellar death. Planets have also been found in dense stellar clusters, where close encounters between stars might be expected to disrupt planetary systems. The discovery of planets in such environments suggests that planetary systems are more robust than previously thought, capable of surviving in conditions that would seem to preclude their existence. The diversity of known exoplanets continues to expand as detection methods improve and surveys cover more of the sky. Each new discovery adds to our understanding of how planetary systems form and evolve, while also raising new questions about the processes that shape these distant worlds. The exoplanet population we have discovered so far is certainly biased toward planets that are easiest to detect, meaning that the true diversity of planets in the galaxy is likely even greater than what we have observed. As you let these images of strange worlds drift through your mind, consider that we are living in a remarkable era of discovery. Within a single human generation, we have gone from knowing of no planets beyond our solar system to knowing of thousands. We have found worlds of fire and ice, worlds of diamond and lava, worlds that orbit two suns and worlds that orbit none. The universe, it seems, delights in creating planets of every conceivable type, and perhaps many types we have not yet conceived. The story of planetary systems is far richer and more varied than we ever imagined, and we are only beginning to read its opening chapters. Among all the questions that drive the study of exoplanets, None captures the imagination more powerfully than the search for life beyond Earth. Are we alone in the universe, or does life flourish on countless worlds throughout the cosmos? This ancient question, once the province of philosophers and dreamers, has become a subject of serious scientific investigation. Central to this search is the concept of the habitable zone, the region around a star where conditions might allow liquid water to exist on a planetary surface. As you continue to rest peacefully, let us explore the science of habitability and the ongoing quest to find signs of life among the stars. The habitable zone, sometimes called the Goldilocks zone, is defined by temperature. Too close to a star and a planet's surface becomes too hot for liquid water, which boils away into vapour. Too far from a star and the surface becomes too cold, with water freezing into ice. Within the habitable zone, temperatures are just right for liquid water to potentially exist, given the right atmospheric conditions. This focus on liquid water reflects our understanding of life on Earth, where water serves as the essential medium for all known biochemistry. The boundaries of the habitable zone depend on several factors, most importantly, the luminosity of the host star. More luminous stars have habitable zones that are farther out, while less luminous stars have habitable zones closer in. For our Sun, the habitable zone is estimated to extend from about 0.985 to 1.67 astronomical units, placing Earth comfortably within its bounds, and Mars near the outer edge. Venus, at 0.72 astronomical units, lies inside the inner edge of the habitable zone, which may help explain its runaway greenhouse conditions. The concept of the habitable zone is useful, but also limited. A planet's actual surface temperature depends not only on its distance from the star, but also on the properties of its atmosphere. A thick atmosphere with strong greenhouse gases can warm a planet well above what its orbital distance alone would suggest, potentially making planets habitable even outside the traditional habitable zone. Conversely, a planet with little or no atmosphere might be uninhabitable even within the habitable zone, as it would lack the insulation needed to maintain moderate temperatures. Earth's habitability depends critically on its atmosphere, which contains greenhouse gases like water vapour and carbon dioxide that trap heat and raise surface temperatures above what they would otherwise be. Without the greenhouse effect, Earth's average surface temperature would be well below freezing, and liquid water would be scarce. The greenhouse effect thus extends the habitable zone outward, allowing planets at greater distances from their stars to maintain liquid water. However, the greenhouse effect can also work against habitability if it becomes too strong. Venus provides a cautionary example of a runaway greenhouse effect, where positive feedback between temperature and atmospheric water vapour led to ever-increasing temperatures until the oceans boiled away and the planet became uninhabitable. Understanding the conditions that lead to runaway greenhouse warming is essential for assessing the habitability of exoplanets near the inner edge of the habitable zone. Red dwarf stars, also known as M-dwarfs, are the most common type of star in the galaxy, comprising about 70% of all stars. Their habitable zones lie very close to the star, typically at distances of only 0.1 to 0.3 astronomical units. Planets in these close-in habitable zones are easier to detect than planets in the habitable zones of Sun-like stars, making red dwarfs attractive targets for the search for habitable worlds. However, planets orbiting red dwarfs face several challenges to habitability. The close proximity to the star means that planets are likely to be tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. This could create extreme temperature contrasts between the day and night sides, though atmospheric circulation might help distribute heat more evenly. Red dwarfs are also prone to powerful flares that could strip away planetary atmospheres and bathe surfaces in harmful radiation. Despite these challenges, red dwarf planets remain promising targets in the search for life. The nearest known potentially habitable exoplanet, Proxima Centauri b, orbits a red dwarf just 4.2 light-years from Earth. This planet, discovered in 2016, has a minimum mass of about 1.3 Earth masses and orbits within its star's habitable zone. Whether Proxima Centauri b actually possesses conditions suitable for life remains unknown, but its proximity makes it an attractive target for future study. The search for life on exoplanets focuses largely on the detection of biosignatures, observable features that would indicate the presence of life. The most commonly discussed biosignatures are atmospheric gases that are produced by living organisms and would not persist in an atmosphere without continuous biological replenishment. On Earth, the most prominent example is oxygen, which is produced by photosynthesis and would quickly disappear from the atmosphere if life ceased. Oxygen is an attractive biosignature because it is highly reactive and tends to combine with other elements, removing it from the atmosphere. Maintaining a significant oxygen concentration requires a continuous source, and on Earth that source is photosynthetic life. The detection of oxygen in an exoplanet atmosphere, particularly in combination with other gases like methane that would react with oxygen, could be a strong indicator of biological activity. However, oxygen is not a perfect biosignature. Abiotic processes, those not involving life, can also produce oxygen under certain circumstances. Photodissociation of water vapour by ultraviolet light can release oxygen, particularly on planets orbiting active stars. The oxygen produced by this process might accumulate in the atmosphere if hydrogen escapes to space faster than it can recombine with oxygen. Distinguishing biological oxygen from abiotic oxygen will require careful analysis of atmospheric composition and context. Other potential biosignatures include methane, nitrous oxide, and various sulfur compounds that are produced by life on Earth. The simultaneous presence of multiple biosignature gases, particularly those that would react with each other and thus require continuous replenishment, would provide stronger evidence for life than any single gas alone. This concept of looking for chemical disequilibrium in planetary atmospheres guides much of the current thinking about biosignature detection. The James Webb Space Telescope, launched in December 2021, represents a major advance in our ability to study exoplanet atmospheres. Webb's infrared instruments can analyze starlight that has passed through an exoplanet's atmosphere during transit, revealing the spectral signatures of atmospheric molecules. Early Webb observations have already detected carbon dioxide, water vapor, and other molecules in the atmospheres of several exoplanets, demonstrating the telescope's capabilities for atmospheric characterization. While Webb is primarily studying the atmospheres of large hot planets that produce strong signals, it is also beginning to observe smaller, cooler planets that are more relevant to the search for life. The TRAPPIST-1 system, with its 7 Earth-sized planets, including several in the habitable zone, is a prime target for Webb observations. Initial results suggest that at least some of the TRAPPIST-1 planets may lack thick atmospheres, but observations are ongoing and the full picture is still emerging. Beyond atmospheric biosignatures, scientists have proposed other ways to detect life on exoplanets. The vegetation red edge is a sharp increase in the reflectivity of plant-covered surfaces at near-infrared wavelengths caused by the cellular structure of leaves. If an exoplanet were covered with vegetation similar to Earth's, this spectral feature might be detectable in reflected light observations. However, alien vegetation might have different spectral properties, making this biosignature less universal. Technosignatures, evidence of technology rather than biology, represent another avenue for detecting life. Radio signals, laser emissions, or other artificial electromagnetic radiation could indicate the presence of intelligent civilizations. The search for extraterrestrial intelligence, or SETI, has been scanning the skies for such signals for decades without confirmed detections, but the search continues with ever-improving sensitivity and coverage. The question of whether life exists beyond Earth remains unanswered, but the tools and techniques for addressing it are advancing rapidly. Within the coming decades, we may have the capability to detect biosignatures in the atmospheres of nearby exoplanets, potentially providing the first evidence that we are not alone. Even a null result, finding that nearby habitable planets show no signs of life, would be scientifically valuable, constraining theories about the origin and prevalence of life in the universe. As you rest and contemplate these possibilities, consider the profound implications of either outcome. If life is common in the universe, we are part of a vast cosmic community of living worlds connected by the same laws of physics and chemistry that govern life everywhere. If life is rare, we bear a special responsibility as perhaps the only beings capable of contemplating the universe and our place within it. Either way, the search for life beyond Earth is one of the most profound scientific endeavours ever undertaken, and we are privileged to live in an era when answers may finally be within reach. The planets within a planetary system do not exist in isolation. They interact gravitationally with one another, with their host star, and with any remaining debris from the formation process. These interactions shape the architecture of planetary systems over time, determining which configurations are stable and which lead to dramatic rearrangements or even planetary ejections. Understanding planetary dynamics is essential for interpreting the diverse planetary systems we observe and for reconstructing the histories that led to their current states. As you continue to drift peacefully, let us explore the elegant mathematics and complex behaviours that govern the motions of worlds. At the most basic level, the motion of a planet around a star follows the laws described by Johannes Kepler in the early 17th century. Kepler's first law states that planets move in elliptical orbits, with the star at one focus of the ellipse. Kepler's second law describes how planets move faster when closer to the star and slower when farther away, sweeping out equal areas in equal times. Kepler's third law relates the orbital period of a planet to its distance from the star, with more distant planets taking longer to complete their orbits. These laws, later explained by Isaac Newton's theory of gravity, form the foundation of our understanding of planetary motion. In a system with only one planet orbiting a star, Kepler's laws provide an essentially complete description of the planet's motion. The orbit remains stable and unchanging, with the planet tracing the same elliptical path around the star indefinitely. However, real planetary systems contain multiple planets, and the gravitational interactions between these planets introduce complexities that go far beyond the simple two-body problem of a single planet orbiting a star. When multiple planets orbit the same star, each planet feels not only the gravitational pull of the star, but also the gravitational tugs of all the other planets. These planet-planet interactions are typically much weaker than the star-planet interaction, because planets are much less massive than stars. Nevertheless, over long timescales, even weak gravitational perturbations can accumulate and produce significant changes in planetary orbits. The study of these long-term orbital changes is called secular dynamics, and it reveals the slow, graceful evolution of planetary systems over millions and billions of years. One of the most important effects of planet-planet interactions is the precession of orbital elements. The orientation of a planet's orbit in space is not fixed but slowly rotates over time due to gravitational perturbations from other planets. The direction of the orbit's long axis, called the longitude of perihelion, precesses around the star over timescales of thousands to millions of years. Similarly, the plane of the orbit can wobble, with the orbital inclination and the direction of the ascending node changing over time. These precessions are generally slow and gentle, causing no dramatic changes in the planet's distance from the star or its overall orbital shape. The gravitational interactions between planets can also cause their orbital eccentricities and inclinations to oscillate over time. In a system with two planets, the eccentricities of both planets may vary periodically, with one planet's eccentricity increasing while the other's decreases, and vice versa. This exchange of eccentricity occurs because angular momentum is conserved in the system, so changes in one planet's orbit must be balanced by opposite changes in another's. Similar oscillations can occur in orbital inclinations, with planets trading inclination back and forth over long timescales. The timescales for secular evolution depend on the masses and orbital separations of the planets involved. More massive planets produce stronger perturbations and faster evolution. Planets that are closer together interact more strongly than those that are widely separated. In our own solar system, the secular interactions between the giant planets cause their orbital elements to oscillate with periods of tens of thousands to millions of years. These slow variations have subtle but important effects on the inner solar system, influencing Earth's climate through changes in orbital eccentricity and axial tilt. Beyond the slow secular evolution, planetary systems can exhibit more dramatic dynamical behaviors when planets approach certain special configurations. Orbital resonances occur when the orbital periods of two planets form a simple integer ratio, such as 2:1, 3:2, or 5:3. When planets are in or near resonance, their gravitational interactions are amplified because the planets repeatedly encounter each other at the same points in their orbits. These repeated encounters can either stabilize or destabilize the system, depending on the specific resonance and the orbital configurations involved. Mean motion resonances, the most commonly discussed type of orbital resonance, occur when the orbital periods of two planets are related by a ratio of small integers. In a 2:1 resonance, the inner planet completes exactly 2 orbits for every 1 orbit of the outer planet. In a 3:2 resonance, the inner planet completes 3 orbits for every 2 orbits of the outer planet. These resonant configurations can be remarkably stable, with planets remaining locked in resonance for billions of years. The stability of mean motion resonances arises from a self-correcting mechanism. When two planets are in resonance, their conjunctions, the moments when they are closest together, always occur at the same points in their orbits. If one planet begins to drift out of resonance, the timing of conjunctions shifts, and the resulting gravitational perturbations push the planet back toward the resonant configuration. This restoring force keeps the planets locked together, maintaining the resonance despite small perturbations. Our own solar system contains several examples of mean motion resonances. Neptune and Pluto are locked in a 3.2 resonance, with Pluto completing 2 orbits for every 3 orbits of Neptune. This resonance protects Pluto from close encounters with Neptune, even though Pluto's eccentric orbit actually crosses Neptune's orbit. The resonance ensures that when Pluto is at its closest approach to the Sun, Neptune is always on the opposite side of its orbit, far from Pluto. The moons of Jupiter provide another beautiful example of orbital resonance. Io, Europa, and Ganymede are locked in a 4:1 resonance, meaning that for every 4 orbits of Io, Europa completes exactly 2 orbits, and Ganymede completes exactly 1. This 3-body resonance, called the Laplace resonance after the mathematician who first analysed it, has persisted for billions of years and has profound effects on the moons involved. The resonance maintains the orbital eccentricities of the moons, which in turn drives tidal heating in their interiors. Exoplanetary systems have revealed even more dramatic examples of resonant configurations. Some systems contain chains of planets locked in a sequence of resonances, with each adjacent pair of planets in a resonant relationship. The TRAPPIST-1 system, with its 7 Earth-sized planets, displays a remarkable resonant chain in which the orbital periods form a sequence of near-integer ratios. Such resonant chains are thought to form through planetary migration, as planets moving through a protoplanetary disk can become captured into resonances with one another. Planetary migration, the process by which planets change their orbital distances over time, is one of the most important concepts in modern planetary science. The discovery of hot Jupiters, giant planets orbiting extremely close to their stars, provided the first strong evidence that planets do not always remain where they formed. Since giant planets cannot form so close to their stars, where temperatures are too high and solid material too scarce, they must have migrated inward from their birthplaces in the outer disk. Several mechanisms can drive planetary migration. Type 1 migration affects smaller planets that are embedded in a gaseous protoplanetary disk. The planet's gravity creates spiral density waves in the disk, and the gravitational interaction between the planet and these waves transfers angular momentum between the planet and the disk. Depending on the disk properties, this angular momentum transfer can cause the planet to spiral inward, or in some cases, outward. Type 1 migration can be quite rapid, potentially moving a planet significant distances within the lifetime of the disk. Type 2 migration affects larger planets that have opened gaps in the disk by gravitationally clearing material from their orbital vicinity. Once a gap is opened, the planet becomes coupled to the viscous evolution of the disk, migrating inward as disk material slowly accretes onto the central star. Type 2 migration is generally slower than Type 1 migration, but it can still transport giant planets from the outer disk to close-in orbits over the few million-year lifetime of a typical protoplanetary disk. A third migration mechanism, called planetesimal-driven migration, can operate even after the gas disk has dispersed. In this scenario, a planet interacts gravitationally with a disk of planetesimals, small rocky or icy bodies left over from the planet formation process. Each close encounter between the planet and a planetesimal exchanges a small amount of angular momentum. If the planet scatters more planetesimals inward than outward, it gains angular momentum and migrates outward. If it scatters more planetesimals outward, it loses angular momentum and migrates inward. Planetesimal-driven migration is thought to have played a major role in shaping our own solar system. The NICE model, named after the French city where it was developed, proposes that the giant planets formed in a more compact configuration than they occupy today and subsequently migrated to their current positions through interactions with a massive disk of planetesimals. In this model, Neptune migrated outward by a substantial distance, scattering planetesimals as it went and creating the Kuiper belt in the process. The NICE model also explains several puzzling features of the solar system, including the late heavy bombardment, a period of intense cratering that affected the inner solar system about 3.9 billion years ago. According to the model, the migration of the giant planets destabilized the planetesimal disk, sending a shower of impactors into the inner solar system. The scars of this bombardment are still visible on the Moon and other ancient surfaces throughout the solar system. Planet-planet scattering represents another important dynamical process that can dramatically reshape planetary systems. When two or more giant planets form in orbits that are too close together, their gravitational interactions can eventually destabilize the system. the planet's orbits become increasingly eccentric and begin to cross, leading to close encounters that scatter the planets onto new orbits. In extreme cases, one or more planets may be ejected from the system entirely, becoming free-floating rogue planets that wander through interstellar space. Planet-planet scattering can explain the high orbital eccentricities observed in many exoplanetary systems. While planets forming in a disk are expected to have nearly circular orbits, many known exoplanets have highly elliptical orbits that carry them much closer to and farther from their stars than a circular orbit would. These eccentric orbits are a natural outcome of scattering events, which tend to pump up eccentricities while conserving total angular momentum. The Kozai leadoff mechanism provides yet another way for planetary orbits to evolve dramatically over time. This mechanism operates when a planet is accompanied by a distant companion, either another planet or a binary star, whose orbit is significantly inclined relative to the planet's orbit. The gravitational influence of the distant companion causes the planet's orbital eccentricity and inclination to oscillate in a coupled manner, with high eccentricity corresponding to low inclination, and vice versa. The Kozai leadoff mechanism can drive a planet's eccentricity to extreme values, potentially causing the planet to pass very close to its star at the closest point in its orbit. If the planet passes close enough, tidal interactions with the star can dissipate orbital energy, gradually shrinking and circularizing the orbit. This process, called high eccentricity migration, provides an alternative pathway for producing hot Jupiters, one that does not require migration through a gas disk. The long-term stability of planetary systems is a fundamental question in dynamics. Some configurations are stable for billions of years, while others become unstable on much shorter timescales. Determining whether a given planetary system is stable requires careful analysis, often involving numerical simulations that track the orbits of all planets over long periods. These simulations have revealed that even our own solar system is not perfectly stable. There is a small but non-zero probability that the inner planets could experience a dynamical instability within the next few billion years. The spacing of planets within a system is closely related to stability. Planets that are too close together will eventually experience close encounters that destabilize their orbits. The minimum stable spacing depends on the masses of the planets, with more massive planets requiring wider separations. A useful rule of thumb is that planets must be separated by at least several mutual Hill radii to remain stable, where the mutual Hill radius is a measure of the gravitational reach of the planets relative to the star. Observations of exoplanetary systems have revealed a wide range of dynamical architectures. Some systems are tightly packed, with multiple planets orbiting in a compact configuration that leaves little room for additional planets. Other systems are more spread out, with large gaps between planets that could potentially harbour additional, undetected worlds. The diversity of observed architectures reflects the variety of formation and evolutionary pathways that planetary systems can follow. The study of planetary dynamics connects the present-day configurations of planetary systems to their formation histories. By understanding the dynamical processes that shape planetary systems, we can work backward from observed configurations to infer how those systems formed and evolved. This detective work is challenging, as many different histories can lead to similar present-day configurations, but it provides valuable insights into the processes that create the diverse planetary systems we observe throughout the galaxy. As you rest and let these concepts of orbital mechanics drift through your mind, consider the elegant dance of worlds that plays out in planetary systems throughout the universe. Planets circle their stars in paths shaped by gravity, their orbits slowly evolving through interactions with siblings and debris. Resonances lock planets together in harmonious configurations, while scattering events send worlds careening onto new trajectories. The dynamics of planetary systems are complex and beautiful, a cosmic ballet choreographed by the fundamental laws of physics. Every planetary system has a beginning, a middle, and an end. We have explored how planetary systems form from the swirling disks of gas and dust around young stars, and how they evolve through dynamical interactions over billions of years. Now, let us turn our attention to the distant future, to the ultimate fates that await planetary systems as their host stars age and die. The story of planetary systems does not end with their formation. It continues through the entire lifetime of the star and beyond, into epochs so remote that they strain our imagination. As you settle deeper into relaxation, let us contemplate the long-term futures of worlds. The fate of a planetary system is intimately tied to the fate of its host star. Stars do not shine forever. They are powered by nuclear fusion reactions that gradually consume their fuel. The timescale over which a star exhausts its fuel depends primarily on its mass, with more massive stars burning through their fuel much faster than less massive ones. A star like our Sun has a total lifetime of about 10 billion years, of which roughly half has already elapsed. Less massive red dwarf stars can shine for trillions of years, far longer than the current age of the universe. More massive stars may exhaust their fuel in only a few million years. For a star like the Sun, the first major change comes when the hydrogen fuel in the core is exhausted. At this point, roughly 5 billion years in the future, the core contracts and heats up while hydrogen fusion continues in a shell surrounding the core. The energy released by this shell burning causes the outer layers of the star to expand dramatically, transforming the star into a red giant. As the Sun becomes a red giant, its radius will increase by a factor of about 100, engulfing the orbits of Mercury and Venus, and possibly reaching as far as Earth's current orbit. The expansion of the Sun into a red giant will have catastrophic consequences for the inner planets. Mercury and Venus will be swallowed by the expanding stellar envelope and spiral inward due to drag, eventually being vaporized in the stellar interior. Earth's fate is less certain. It depends on details of the Sun's mass loss and expansion that are difficult to predict precisely. Even if Earth avoids being engulfed, it will be scorched by the increased luminosity of the red giant Sun, with surface temperatures rising high enough to boil away the oceans and strip away the atmosphere. The outer planets will fare better during the red giant phase, at least initially. Jupiter, Saturn, Uranus, and Neptune orbit far enough from the Sun that they will not be directly threatened by the expanding stellar envelope. However, the increased luminosity of the red giant Sun will heat these worlds and their moons, potentially causing significant changes to their atmospheres and surfaces. The icy moons of the outer planets, currently frozen solid, might experience temporary periods of surface melting as the Sun brightens. As the Sun continues to evolve, it will eventually exhaust the helium fuel in its core and enter a phase of instability. The outer layers of the star will be expelled in a series of thermal pulses, creating a beautiful but short-lived planetary nebula. The exposed core of the star, no longer able to sustain fusion, will contract and cool to become a white dwarf, a dense stellar remnant about the size of Earth, but with a mass comparable to the Sun. The white dwarf Sun will initially be very hot, glowing blue-white, but it will gradually cool over billions of years, eventually fading to invisibility. The formation of a white dwarf dramatically alters the gravitational environment of the planetary system. As the star loses mass during the red giant and planetary nebula phases, its gravitational pull weakens, and the orbits of surviving planets expand. A planet that orbited at 5 astronomical units before the mass loss might find itself at 10 or more astronomical units afterward. This orbital expansion helps protect the outer planets from the immediate effects of stellar evolution, moving them away from the cooling white dwarf. White dwarf planetary systems are not merely theoretical constructs. Astronomers have found evidence for planets and planetary debris around many white dwarfs. Some white dwarfs show spectral signatures of heavy elements like calcium, magnesium, and iron in their atmospheres. Since heavy elements should sink rapidly below the surface of a white dwarf due to its intense gravity, their presence in the atmosphere indicates ongoing accretion of rocky material. This material is thought to come from asteroids or planetary fragments that have been perturbed onto orbits that bring them close to the white dwarf, where they are tidally disrupted and accreted. In some cases, astronomers have detected intact planets orbiting white dwarfs. The first confirmed example, discovered in 2020, is a giant planet orbiting the white dwarf WD 1856 Pli-534 at a distance of only about 0.02 astronomical units. This planet must have migrated inward after the star became a white dwarf, as it would have been engulfed during the red giant phase if it had always been so close. The discovery demonstrates that planetary systems can survive stellar evolution and continue to evolve dynamically even around stellar remnants. For planetary systems around more massive stars, the end states are even more dramatic. Stars with masses greater than about 8 times the Sun's mass end their lives in supernova explosions, catastrophic events that release more energy in seconds than the Sun will produce in its entire lifetime. The intense radiation and blast wave from a supernova would likely destroy any planets in the inner system and strip the atmospheres from planets farther out. Any planets that survive would find themselves orbiting a neutron star or black hole, the compact remnants left behind by the supernova. Remarkably, planets have been found orbiting neutron stars, the rapidly spinning, incredibly dense remnants of supernova explosions. The first exoplanets ever discovered, announced in 1992, orbit the pulsar PSR B1257+12. These planets may have formed from debris left over after the supernova, coalescing from a disk of material that surrounded the newly formed neutron star. Alternatively, they might be the remnants of larger bodies that survived the supernova and were subsequently modified by the extreme environment. The very long-term future of planetary systems, extending far beyond the lifetimes of their host stars, involves processes that operate on timescales of trillions of years. White dwarfs cool gradually, radiating away their residual heat into space. Over timescales of perhaps 10 to the 15th years, white dwarfs will cool to the point where they no longer emit significant radiation, becoming cold, dark objects, sometimes called black dwarfs. The planets orbiting these black dwarfs will be frozen and dark, illuminated only by the faint glow of distant galaxies. On even longer timescales, gravitational interactions will gradually reshape planetary systems. Close encounters between stars, rare but inevitable over sufficiently long times, can perturb planetary orbits and even strip planets from their host stars. Over timescales of 10 to the 19th years or more, most planets will either be ejected from their systems by stellar encounters or will spiral inward and merge with their stellar remnants due to gravitational radiation. The ultimate fate of most planets is to become free-floating objects drifting through an increasingly cold and empty universe. These far future scenarios may seem bleak, but they are also humbling reminders of the vast timescales over which the universe operates. The planetary systems we observe today, including our own solar system, are snapshots in an ongoing story that began billions of years ago and will continue for billions or trillions of years into the future. The worlds we know are temporary configurations, destined to change and eventually disappear as the universe continues its long, slow evolution. Yet there is also beauty in this impermanence. The fact that planetary systems have finite lifetimes makes their current existence all the more precious. The Earth, with its oceans and continents, its forests and deserts, its teeming life, is a fleeting wonder in the cosmic story. The other worlds of our solar system and the countless exoplanets orbiting distant stars are all temporary arrangements of matter and energy, brief patterns in the endless flow of cosmic time. As you rest and contemplate these distant futures, let the vastness of time wash over you like a gentle wave. The story of planetary systems is a story of change, of formation and evolution, and eventual dissolution. But it is also a story of persistence, of worlds that endure for billions of years, providing stable environments where complexity can emerge and flourish. We are part of this story, inhabitants of a small rocky world orbiting an ordinary star, witnesses to a moment in the long history of our planetary system. The study of planetary systems stands at an exciting threshold. The discoveries of recent decades have transformed our understanding of how planets form, how common they are, and how diverse they can be. Yet for all that we have learned, far more remains unknown. The coming years and decades promise a wealth of new observations, new missions, and new discoveries that will continue to reshape our picture of planetary systems throughout the universe. As you drift peacefully towards sleep, let us look ahead to the future of planetary exploration and the questions that drive the continuing quest. The James Webb Space Telescope, which began science operations in 2022, represents a transformative capability for studying exoplanet atmospheres. Webb's large mirror and infrared instruments allow it to collect and analyze light from exoplanets with unprecedented sensitivity. By observing the spectra of starlight that has passed through exoplanet atmospheres during transits, Webb can identify the molecular constituents of those atmospheres, including water vapor, carbon dioxide, methane, and potentially biosignature gases. Early Webb observations have already yielded remarkable results. The telescope has detected carbon dioxide in the atmosphere of a gas giant exoplanet, the first definitive detection of this molecule in an exoplanet atmosphere. It has characterized the atmospheric composition of several hot Jupiters, revealing the presence of water vapor, carbon monoxide, and other molecules, and it has begun to probe the atmospheres of smaller, cooler planets that are more relevant to the search for habitable worlds. The TRAPPIST-1 system is a prime target for Webb observations. This nearby system of 7 Earth-sized planets, several of which orbit within the habitable zone, offers an unparalleled opportunity to study potentially habitable worlds. Webb observations are already providing constraints on the atmospheres of these planets, determining whether they possess thick atmospheres that could support liquid water or whether they are bare, airless rocks. The results will have profound implications for our understanding of habitability around red dwarf stars. Beyond Webb, several future space missions are being planned or developed to advance exoplanet science. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a large survey for exoplanets using the gravitational microlensing technique. This survey will be sensitive to planets that are difficult to detect by other methods, including planets in wide orbits and free-floating planets that do not orbit any star. Roman will provide a statistical census of the planet population in the outer regions of planetary systems, complementing the inner system focus of transit surveys. The European Space Agency's Plato mission, planned for launch in 2026, will search for transiting planets around bright, nearby stars. Plato's primary goal is to find Earth-sized planets in the habitable zones of Sun-like stars, the most Earth-like planets accessible to current technology. By focusing on bright host stars, Plato will identify planets that are well suited for atmospheric characterization with Webb and future telescopes. The Atmospheric Remote Sensing Infrared Exoplanet Large Survey, or ARIEL, is another European mission planned for launch in 2029. ARIEL will conduct a systematic survey of exoplanet atmospheres, observing hundreds of planets, to understand the diversity of atmospheric compositions and the processes that shape them. By studying a large sample of planets, ARIEL will reveal statistical trends and correlations that are impossible to discern from observations of individual systems. Looking further ahead, astronomers are developing concepts for even more ambitious missions that could directly image Earth-like planets around nearby stars. Direct imaging of small rocky planets is extraordinarily challenging because such planets are billions of times fainter than their host stars and appear very close to them in the sky. Overcoming this challenge requires either a space telescope with an internal coronagraph to block starlight, or a separate starshade spacecraft that flies in formation with the telescope to cast a shadow over the star. The Habitable Worlds Observatory, currently in the early planning stages, is envisioned as a large space telescope capable of directly imaging and characterizing Earth-like planets around nearby Sun-like stars. Such a mission could search for biosignatures in the atmospheres of potentially habitable worlds, potentially providing the first evidence for life beyond Earth. The technical challenges are formidable, but the scientific payoff would be immense. Ground-based observatories are also advancing rapidly. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, making it the largest optical telescope ever built. This enormous collecting area will enable observations of exoplanet atmospheres with unprecedented detail, potentially detecting biosignature gases in the atmospheres of nearby rocky planets. Other extremely large telescopes under construction, including the 30-meter telescope and the Giant Magellan Telescope, will provide similar capabilities. The search for biosignatures is not limited to atmospheric observations. Future missions may search for signs of life through other means, such as detecting the spectral signature of surface vegetation or identifying artificial structures or signals produced by intelligent civilizations. The search for extraterrestrial intelligence continues to scan the skies for radio and optical signals that might indicate the presence of technological civilizations. Using increasingly sensitive instruments and sophisticated analysis techniques. Within our own solar system, exploration continues to reveal new details about the planets and moons that share our cosmic neighborhood. NASA's Europa Clipper mission, scheduled for launch in 2024, will conduct detailed observations of Jupiter's moon Europa, investigating its ice shell, subsurface ocean, and potential habitability. The mission will fly past Europa dozens of times, using radar, cameras, and other instruments to characterize this intriguing world. The Dragonfly mission, planned for launch in 2028, will send a rotorcraft lander to Saturn's moon Titan. This innovative mission will take advantage of Titan's thick atmosphere and low gravity to fly from location to location, exploring diverse terrains and searching for signs of prebiotic chemistry or even life. Titan's organic-rich surface and subsurface ocean make it one of the most promising places in the solar system to search for life beyond Earth. Mars continues to be a focus of intense exploration. Multiple rovers and landers are currently operating on the Martian surface, studying the planet's geology, climate, and potential for past or present life. The Mars Sample Return Mission, a joint effort between NASA and the European Space Agency, aims to bring samples of Martian rock and soil back to Earth for detailed analysis. These samples could provide definitive evidence for past life on Mars, if such life ever existed. The outer solar system remains largely unexplored, with only brief flyby missions having visited Uranus and Neptune. Scientists are advocating for a dedicated mission to one or both of these ice giants, which would provide detailed observations of worlds that are quite different from the gas giants Jupiter and Saturn. Such a mission could reveal new insights into the formation and evolution of ice giant planets, which appear to be common in the galaxy based on exoplanet surveys. The continuing quest to understand planetary systems is driven by fundamental questions about our place in the universe. How do planets form, and what determines the architecture of planetary systems? How common are habitable worlds, and what conditions are necessary for life to arise? Are we alone in the universe, or does life flourish on countless worlds throughout the cosmos? These questions have captivated human imagination for millennia, and we are now developing the tools and techniques to begin answering them. As you drift towards sleep, consider that you are living in a remarkable era of discovery. Within your lifetime, we have gone from knowing of no planets beyond our solar system to knowing of thousands. We have sent spacecraft to every planet in our solar system and to many of their moons. We have peered into the atmospheres of distant worlds and begun to search for signs of life beyond Earth. The story of planetary systems is still being written, and each new discovery adds another chapter to this grand cosmic narrative. The universe is vast beyond comprehension, filled with countless stars and planets, each with its own story. Some of those worlds may harbour life, perhaps even intelligent beings who gaze up at their own night skies and wonder about the universe just as we do. The search for those worlds and for the answers to our deepest questions continues with each passing day. And as you rest now, peaceful and relaxed, know that the quest goes on, driven by the same curiosity and wonder that has always propelled humanity to explore the unknown.